Hello, what's going on? What is going on? What is going on is I need to get some duct tape so I can make sure that my secondary camera stays in the correct position. Good thing I have plenty of duct tape and like scissors and stuff. So basically, because I don't have good tripods and stuff, and because civilization is kind of ending, so I can't actually go to the store to get a tripod, because the store isn't open even if I wanted to, because California, even though that doesn't actually help solve any problems. I am resorting to whatever works. So I have this fine mechanism where I have a webcam duct taped to a microphone, and then if I put the webcam over the desk in just the right way, I could write on a piece of paper to draw diagrams, because there's no way to draw diagrams on a computer that's reasonable, even though it's the year 2020. So that is where we are at. Okay, I will tweet the link out. Time for some UML. I really don't think that that's what time it is. I'm just tweeting out a link. So what's going on, everybody? The Microsoft Whiteboard app is not bad. I simply don't believe you. I don't believe anyone who says that Microsoft anything is not bad. That's just not the reality we live in. We're not going to talk about anything sophisticated in rendering. I'm just going to explain the basics of what we're doing. Like super basics. Super basics. Any pre-stream questions? We're going to give people another 5 or 6 minutes. WSL2 is a step in the right direction. Well, you and I have very different ideas about what the right direction is. Very different. What made I want to explain it? Because I just felt like it. Sometimes, like, I was like, well, if I'm going to explain what I'm doing today to people, it might be interesting. And if I'm going to explain like if people, like I was going to do a normal stream, all right? And then I was like, oh, if I do the stream, I should explain what's going on because it's kind of coherent thing to talk about. And then I said, if I'm going to do that, it might be fun to just do a more full explanation for people who don't really know how this stuff goes, right? So yeah. Will this go up on YouTube? Probably. Maybe not. DX11 or DX12, you need to choose one of these two as an API for your next game. That is not how it works. The world we are in, whether you like it or not, you have to either support 5 rendering APIs for your next game, or you don't ship your game hardly anywhere. That is the universe of computers that we have built. It's not a question of picking one. You have to do all of them. Why not just OpenGL? Because it's garbage. And it also doesn't run most places. So it's garbage that you can't use on a lot of platforms anyway. Okay, the camera, we may need to increase the tension on the camera doohickey. The combined camera microphone doohickey. Are there any actual real questions that we should answer, or should we just launch into talking about what we're talking about? What is your crappy hot take on random topic X that I wasn't thinking about yesterday and won't be thinking about tomorrow? Like, you don't want to ask that kind of question, because if you're thinking about that kind of stuff all the time, you're just filling your own head with garbage. And the fact that you're filling your own head with garbage means that it's hard for non-garbage to get a foothold. Okay? So like it bothers me that so many people ask me that kind of thing. Because it just means a lot of people, I don't know, a lot of people are not putting themselves even in a position to have a reasonable life. Like, I don't even know. Okay, I'm going to set up a little something that we could use to demonstrate things. And then maybe we'll start. Maybe. And then maybe this thing. Okay, let's get rid of all the rivers from the map. Okay. This is really not going to stay elevated. Like, I can't even tighten this microphone stand enough that it won't. Maybe I need to get a microphone stand made in Taiwan instead of wherever this was made. Okay, let's talk about some things today. Welcome, everybody. We're gonna first do some video game. So, working on this game. Actually, let me step back. Actually, no. Where do we start? Where do we start? There has been some stuff in this game that I'm working on that has been broken for a long time. And sometimes you just don't want to deal with things that are broken. And so you just let them slide forever. But then eventually the time comes to fix those things and you feel really good even about the opportunity to fix it, even though it's a pain, because you're finally going to fix a long-standing issue. Oh, man. I think I introduced a frame rate problem into the game. This might ruin our ability to demo. Let me delete some things in hope that it helps. I actually also, just before the stream, made some changes. So like, well, we have a high frame rate. It's dropping very quickly. Okay, I screwed something up. Well, we're just going to reset the level every few minutes, and that'll be fine. So last night I made a mistake where we were letting an array grow every frame, and so that's probably happening as well. Wow, it just goes down real fast. I almost want to stop and fix this, but I think it is. Yeah, okay, we'll just live with it for a bit. No, it's not because of the second camera. It's definitely a bug in the game. That's important for me to fix tonight. Okay. Camera's lagging too. Maybe it is camera. Maybe the machine is just dying. I don't know. Yeah, so the game's actually doing okay now, and now it's just the camera. So maybe because this is a modern computer in the year 2020, it cannot handle multiple things happening. Okay. Let's start over and I'll explain the problem and then we'll shut off the game and maybe we'll go faster. So, we've been making this game. I've been working on it for a while, and it's a puzzle game where you walk around, you manipulate various objects, and of course we want the game to look interesting, so objects have various properties. So for example, I have these stone blocks that I could push around, like I could push this into the water and it like sinks in there. Don't mind the weird graphics showing through the things. That's an aspect of games not really being done. I can undo what I did. I can go push this crystal into the water. Now, this crystal looks weird. Like it looks like it's in the water, but it doesn't look like it's in the water. And what's going on there? And actually the same thing is going over here. This little orange, this is like an orange energy field thing. If we zoom in to it, I don't know if you could tell what that is. But you know, it's actually sunk into the water and it doesn't look like it is, right? And so this is actually a problem that's been in the game for a long time, because when you try to build levels that have like a lot of things in them, it can be hard to tell what's going on. So let me, for example, these things are going to all fall into the water as soon as I start moving around, right? So let's just do that. And so with the two stones, even though the opacity of this water is not set very high, the two stones, you can see where they are. And you could figure out if you're trying to solve a puzzle, like, oh, that's where I can stand. If I'm going to try to push something along the water between those, I see where it needs to go. Whereas with the things that are in the water, or the crystals that are in the water, it's like you can't really see what's going on. And especially for some camera angles, some levels have lower or higher camera angles. If your camera angle is like this is really suddenly very annoying, right? Because it looks like they fill two squares. So like mentally, it's hard to reason about this level. Whereas if they were just attenuated by the water, like you see with the stones below there, then this wouldn't be a problem. You might still say, oh, this level isn't that clear, but you could make the water more opaque and it would be easier to see what's going on. So this is the kind of thing that you deal with during game development all the time. It's like when the game's not done, when it's at the very beginning, you have all kinds of problems, you know, and you can't solve them all at once, so you procrastinate on some. So we've been procrastinating on this one for a really long time, but I think it's time to fix it, because sometimes when you let things go for too long, it just feels really bad. Part of the reason we didn't fix this one sooner is that there's the whole question of like, what exactly are we going to do it? How is the rendering going to work? Do we have to change it for different platforms and different rendering APIs? And I'll get into what exactly this is, what exactly the problem is, and what solution I'm going to implement. I decided I'm just going to solve it even if we have to change the solution later, because just having something that's close is a lot better than not. In terms of designing the game, knowing how it feels, knowing how hard the puzzles are, right? That's the thing, is like you can't tune your game if your puzzles are artificially difficult, because it's hard for people to look at the screen on particular levels and decode even what is happening spatially, right? So at some point in development, you need to start solving this kind of a problem. So that's the background. So I woke up this morning and said, okay, I'm finally going to solve this problem that's been there for years, literally years now. And so I said, well, I'll do a stream and I'll just give a little explanation of what the problem is, right? And then I said, well, if we're going to give a little explanation, like why not just give a big explanation, giving all the background that's suitable for beginners and everybody? And then we could put that on YouTube and maybe people can use that as a resource, because, you know, in the same way that I get annoyed by all these weird, picky questions that don't represent, like people ask questions all the time that don't represent, like if the questions were answered, they don't represent the gain of any kind of deep knowledge. Like if people ask, what rendering API are you going to use for the game? It's like, well, it doesn't matter, honestly. Right? That's not, like if you're a beginner or you want to get into games, or you want to be an expert at games, you want to be able to do a good job, that is not the kind of question that you should be asking. And it's not really the kind of question I should be spending that much time talking about, right? And it's not just that particular question, but there's all sorts of questions in that avenue, right? And so what I want to start talking about is actually things that actually matter, right? Why is this a problem? What exactly is going on here? And so forth. And so this explanation might take a long time, but hopefully when it's done, it'll be a resource for people, and I don't know, and we'll have done something good in the world this week. So I'm just going to start giving an intro. I'll maybe stop every 5 or 10 minutes. I don't know how long this is going to go, right? So we'll maybe pause, we'll do questions, and then we'll blast ahead and so forth. etc. So now I'll start by saying that the reason that this orange force field and these crystals don't look right is that they are flagged as transparent materials. And everything else in the scene is opaque. So you're supposed to be able to see things in the background through both of these. You can't actually, for the most part right now. That's because the settings on the game have been tweaked. But like, okay, if you look through this orange thing, you can see sort of the stone behind it. And under, because we just changed all our lighting parameters, things are weird. But when we reset those, or when we calibrate those, it'll make more sense that these are translucent objects, even though they look kind of mostly opaque right now. If I had prepared for a day for this demo, we might have done that. Okay, so let me talk for a bit about what do we do when we render a scene like this, okay? And I guess we'll start maybe drawing on some piece of paper to do that. And we'll see. Okay, so I've got my very high-tech drawing situation here. Maybe we'll do this, and I'll make me a little bit bigger, and then maybe I'll keep the game down in the... No, that's going to be a problem. We're not really going to be able to see anything useful from that. I could do this. I don't know how useful that's going to be. We'll see. Okay. So, when we do a game scene like this, what is going on from a high level? Like how do games work? So a lot of the things I'm going to say now apply to the way almost every video game works. We're going to talk about, I don't even know what the correct technical term for it would be. I guess projected and rasterized rendering. There are other ways that you could render a scene, for example, using ray tracing, which is a little bit different, like, again, because we're flooded in all this marketing that doesn't mean anything, right? There's like all this RTX stuff and like, oh, ray tracing is here. That's not... Most of the games that use that functionality are not actually rendering the scene via ray tracing, right? They're using ray tracing on the GPU to do some added functionality, which they then render into the scene in a traditional way. You could render by ray tracing if you wanted to, but it would be slower than what we currently do by a substantial amount. But that would solve the problem that I'm going to go in here with transparency, right? So it might be a nice thing to move to a completely ray traced architecture in the future, but we're not there now for most games that ship on most platforms. We are still using the same architecture that we've been using since about 1995, so 25 years. It's just more complicated today. It has a lot more features and has a lot more needless complexity. All right, so someone says, can't you just change the order in which they're drawn so the water is always on top? You could do that, but these objects are actually poking out of the water. So right now, it could only be either above or either below, or completely above or completely below. Let's talk about why. Okay, so how does rendering work in a video game? Like when you see a big scene like this full of stuff, what is going on, right? So what is going on is you have a window, right? You have a window on your computer and it's got a bunch of pixels. Let's pretend these grid squares are the pixels. Actually, the pixels are much smaller, but visualization, right? So it's just like drawing 2D graphics at the very lowest level is pixel by pixel. You're like, I want this one to be this color. I want this one to be that color. I want this one to be that color, right? I want that one to be that color. You know, that is all in principle that we're doing, is doing this operation for every single pixel on the screen. Well, why do we have all this complexity on top of that? Because this is how software used to work. It used to just go in a loop and figure out the color for every pixel on the screen and do it. And it's really easy to think about how that works. You know, for something like just bitmap rendering or font rendering or something. 3D is more complicated because you have to figure out, say I want to have a dude like my little dude who's moving around here, and I want to put him somewhere on the screen. How do you go from that to all these little pixels? Well, how deep do we want to go into this? Let's go a little bit, right? You can do some math to figure out, like, well, this guy is at a certain position in 3D space, and so we do some math to figure out where he goes in 2D space. So we've got like some guy here. That doesn't still go all the way to pixels, and we'll talk about that in a minute, but let's talk about the math and where it comes from, just because a lot of people don't know this, right? It's very basic information, but a lot of people don't know it. Oh, are we having a fail? Back. Okay, we'll pause for a second. Hopefully people hit reload. Okay. We're also recording this locally, by the way, so, oh man. Let's use this pause to turn off autofocus on the webcam because it's freaking out. Okay, everybody, I'm trying to click, because it's the year 2020, I'm trying to click configure video on the webcam and it won't do it. So like, I guess I can't turn off autofocus. Sorry. Like, this is a $4,000 computer. I can't do anything with it. Oh wait, there's a window somewhere. It showed up on this monitor underneath all the other windows. Okay, great. Camera control, no autofocus, and all right, so closest focus, great. So that shouldn't freak out anymore. All right. So back to the topic. So how do we know where this guy is on the screen? And we'll sort of draw a lower dimensional viewpoint. You know, like what's happening when you look, why is this still up? Oh, I guess it popped up 17 times every time I click the button. Great. I hope, yeah, you guys can kind of see that. That's how many times I click the button trying to get the window to appear. So we have this idea. So, you know, when we're drawing a scene, a rendered scene in a game, we're emulating what it's like to be somebody moving around in a 3D world, right? And so if you're standing somewhere looking at a scene, you're looking out with your two eyes, and right now I'm looking out my window and I see a bunch of trees and buildings and all that. And how does that actually work? Well, let's simplify and pretend you have only one eye, right? How does that actually work? It's actually really complicated and involves all sorts of internal brain stuff that we don't try to emulate. But we have a simplified model that helps us put something on the screen that's at least somewhat like what you see when you look out. And it works like this, right? So you have a place where your eye is, or the camera. This is where you're seeing the world from, right? So this is in a different This is not related to where the screen is at all. This is a different universe. You have some imaginary 3D universe where you have an eye or a camera or something, right? We're just going to put a little eyeball with a, I don't know. So, and light is coming into the eye from the world outside. And one thing about light is that when gravity isn't too strong, it goes in a straight line, okay? So if your model is that you're looking at the world and there's like a building over here and there's a tree over here, right? And all these sorts of things. There's like a little bunny rabbit. I don't know how to draw a bunny rabbit, but I wasn't even trying at the beginning, and then I was like, I'll do a bunny rabbit, right? Okay, so you have some stuff like this. Okay. Whatever is in your world that you're trying to see. So how do you see it? Well, light is coming from the sun. It's hitting every surface. Light is bouncing off all of those surfaces. And it's actually going everywhere, okay? The light that's bouncing, so like you have the sun, right? Light is hitting this point from the sun. It's hitting this point. It's hitting this point. It's hitting this point. The sun is shining everywhere, and every one of these is bouncing everywhere. So like it's the light that hits this corner of the building is going everywhere, and the light that hits here is going everywhere. All right? See that? So there's all sorts of light. But once in a while, very, very rarely, a small portion of this light happens to go in exactly the right direction to land in your eye. Okay. Same thing, you know, some of the light that's bouncing around hits the ear of the bunny rabbit, right? And actually, there's light coming from all directions that hits the ear of the bunny rabbit. And then that bounces outward in all directions. And on very rare occasions, one of those goes in the right direction to go into your eye. Okay? And then that's true for everything in the entire scene, right? Someone says, if all points bounce everywhere, it is not rare at all, but a given. Well, it is a given, but it's also the vast minority of cases. Almost all light doesn't go into your eye, right? It's a given that some will, but almost none does. All right? So, and that's true everywhere in your visual field, you see something, right? And everywhere that you see something, it's light came from that thing into your eye. All right? So you can think of like, there's all these rays that go out. And it's important they're straight lines, right? So for reasons that have to do with basically quantum field theory that we won't really go into, even though it sort of is the case that the light goes off and squiggles around through the universe and comes into your eye, that's not actually what we see on the level of the macroscopic universe. We always see the straight line path. Why? Because the straight line path is the minimum, it's the one pathway that doesn't have a symmetric pathway that'll deconstructively interfere with it. Okay, so actually it's even crazier. Like if you think it's crazy that light comes from every point and bounces off this corner in a straight line to every other point, it's way crazier than that. It's actually, it goes over every possible pathway. But we only see the straight lines in the macroscopic universe. Like I said, this is a whimsical explanation to some degree, so we're going off into things you don't necessarily need to know. All right. People are mentioning there's a very good Richard Feynman speech on this topic, and that is the case. I've seen that one. Okay. Rendering video games in real time is all about simplifying. We really don't need to do all the crazy arbitrary pathways for every photon. In principle, we only need to do these straight lines, but we're not even really going to do that. Okay, so what are we going to do? well, let's start talking about this again. So the model is you have your eye. This pen is going to run out on me. I feel it. I think my video driver just crashed, like the game restarted for some, I don't know what happened there. It looks like my eye is wearing a baseball cap here, whatever. That's like an eye, I don't know. It's like a head with a little dot. So you have your eye and there's light coming in all directions in straight lines. So you have like this fan out of rays. So of course I'm drawing this in 2 dimensions, right? This is all light coming toward you. I'm drawing this in 2 dimensions, but of course in a 3-dimensional world, this would be like a volumetric cone going out in all directions, all right? So now, how do we use this in this model? What do we do to put pixels on the screen that'll make any sense? Like what even do we do? And the answer is, well, again, we're trying to model something that makes sense to your brain, right? So if I'm sitting here and I'm in front of a computer monitor and I'm looking at the computer monitor and I want what's on the computer monitor to be like a world that I'm looking into, which is what we're trying to do, then, well, there's these straight lines that go from my eye out to various points on the monitor. And then if you were to extend those lines into this imaginary world, you would see the different objects in the imaginary world, like the rocks and trees and whatever, right? And so what we do in this model is we say, well, you are actually in the real world. You're looking at a computer screen. It's got a little bit of a bezel. So like this is the bezel where there's no pixels, right? And then here's the screen. And then these rays are coming in from this imaginary world on the other side of the screen. All right. Well, what does that mean? So if I've got a building, if this is ground level, my eye is exactly at the, no, let's just say my eye is exactly on the ground. That's kind of weird, but whatever. So we've got this building here and I see the upper corner of the building. It's got like a satellite dish on it. Okay. So I'm seeing this upper corner of this building. How do we know where to put that on the screen? Let's say we've got a fully modeled 3D world where we have these objects and we have some representation of the objects that tells us where they are in the imaginary world. How do we put that pixel on the screen? And the answer is you can do a little bit of trigonometry. The fact that this is a straight line tells you the answer, all right? Here's what you do is you say, well, here's the trick here for a second is this eye is going to be simultaneously my position in the real world, but also in the imaginary world. So like we're fusing it for a second. And I'm going to say, okay, in the imaginary world, I'm somewhere here on the ground or just above the ground. And here's this building. And there's this screen between us that's going to have the pixels. And the screen, well, it's in this 2D diagram, it's a line, right? In a 3D diagram, it would be a rectangle in space that you're looking through. It's like you're looking through a camera or something. Or like if you're holding your cell phone in front of you and that's got a camera on it that just shows you what's behind it, it's like that. It's like you're looking around like this, okay? So I'm looking around like this, and if I see the corner of the building, it's because there is this triangle, right? Between, let's say I'm looking straight in this direction now. I'm going to draw a back arrow here. We're going to say this is sort of the central axis of my eye where I'm looking, which is also the middle of the screen. All right. And then this is the corner of the building. And that makes a triangle. Okay. Well, what good does that do? Well, the thing is, because this screen is a flat plane, this also makes a triangle. So we have a little triangle here, and then we have a big triangle here. And from beginner geometry class, you might remember there's like this law of similar triangles. All right. So let's call, this is very unconventional notation, but let's call, I don't know, let's call this D here is like the distance along the direction that you're looking to like the base of the building. This is a little bit weird because like I'm not looking directly at the corner. I'm looking like parallel to the ground, right? So this is D, is this distance, right? And then this H is the height of the building, right? And then, so we're going to say D prime is the distance between your eye in the real world and the screen, which we don't actually know most of the time, unless you've got some weird, like, remember how they did the things on the Wiimote where they did like reverse tracking and you could move your head around? You could do that, but we don't usually do that. Usually when you're playing a video game, we just say, well, you're somewhere in front of the screen and we don't care, right? But in the virtual world, we do care. So like, here's the distance between your eye and the camera, right? And then here, this H here, I've drawn this a little bit too small, maybe. Hopefully you get the idea. We can blow it up if people are confused. But this gives you the coordinate on the screen above the middle where you should draw the pixel for this corner of the building, right? Does that make sense at all? You can go back and watch it on YouTube like 5 times. Let's zoom it in a little bit. We'll repeat it and zoom it in because this is actually, I mean, it's very fundamental, right? So again, let's skip a couple pages, get rid of the ink schmutzes. All right, so you have your eye, right? You have your screen, which we're going to make pretty big this time and close. Remember how mom said don't sit too close to the TV? Well, rip. So I've got my eye and I've got the screen and then I've got my building that's out here, right? And so if we're going to say, let's not even pick the top of the building this time. Let's say like I'm looking at this window, then, or actually, so I'm looking horizontal to the ground, let's say, okay? But this window is in my field of view. All of this building is in my field of view because my field of view, actually, what is my field of view? It is the cone that goes from my eye to the upper and lower parts of the camera and then extends beyond those into the virtual world, right? Okay. So that's everything that I can see. It includes this building and, you know, the guy throwing a Molotov cocktail on it and like, you know, looting the target over here and whatever. So, so when I see, you know, somebody stealing a flat screen TV from the 3rd story of this building, where is that on the screen? And the way you find that is you draw a line toward the guy stealing the flat screen TV, okay? And again, you use this triangle identity, right? So we'll just redraw here, although the guys here are going to get in the way. So this D that I was drawing before is the entire distance. You know what? Let me get another color pen. I know I have some. The thing is, these pens are years old and I never use them. Okay. And I've already drawn a big black pen line here. Okay. So this D, this basically isn't really a different color. It's not helping. Well, once upon a time, I had a bunch of different colored pens, but I think they're gone. We're just going to go ahead and, oh, I've got this blue ballpoint right here. Let's see. That's a little bit different. So this entire distance from there to the eye, right? Let's ignore this guy. That's D, right? And then this here was H, right? Was this entire distance. Wow, this is really ugly. Right, and so then this littler distance in here from the eye to the screen, here, this is D prime, and then this is H prime. And so this law of similar triangles just says the following. Oh no, sorry, I drew to the top of the cone. Can't erase this. Okay, from the point where this ray intersects to the axis that you're looking along is H prime. Sorry. Well, this really didn't help. Okay, so similar triangles just means the following thing. D prime over D, or however you want to write the fraction, equals H prime over H, right? So if you know the height H of where the window is in the real world, and you know the distance D, and then you also know D prime, how far is the camera in the virtual world from the eye, then you know 3 of the 4 things in this thing. So you say H prime, you just solve for H prime, right? H prime equals H times D prime over D. Very, very simple math. And this is how you figure out where things go on the screen. You don't have to, it's actually not that intimidating. If you sit down and look this over a few times, it'll totally make sense. I apologize that I didn't draw it better. What is D prime usually set? That's a good question. The answer is as small as you can get away with. But that might not be as small as you would like, because there end up being numerical accuracy issues if you put this plane too close to the eye, right? But if you put it too far from the eye, then some other bad stuff might happen. So I don't know if you've ever seen games. I mean, you surely have, but you know, where you walk up and if you get really close to an object, you can almost see like part of it is cut off and you can sort of see into it. And that happens because maybe I've got some square box here, right? And the math that we do for 3D projection doesn't like it when you go behind this plane. And so we do this thing called clipping where we cut the object at the plane. And so if the border of a solid object goes beyond this plane, that's no good, right? So if this plane is too far out, then you want to prevent people from getting close enough that the plane ever intersects with a solid object. But that means you're maneuvering this big giant volume through the world and you get stuck all the time and stuff, right? So you actually want this plane to be as close to the eye as you can get it. Why does it not just get out of the screen? Because, let me see if I can explain it from this. Sometimes I have to think about things for a while before I can explain them better. I can explain a related thing easily. Okay. So you know, I started out by just saying we're trying to just do something that puts pixels on the screen that is kind of compatible with the image that forms in your head of when you look around at the world, right? And so we ended up with this thing where we divide by this distance to the object, right? You say the height of the particular point that I want to see divided by the distance along the direction I'm looking, right? Times this particular number, right? Gives me the pixel on the screen. But okay, this divide, it's a little bit weird. Like we've successfully made this model that does something that we like, but it has some weird properties. For example, imagine that we just do this for every object in the world, right? And we do this divide. What this divide is doing is projecting points along this line onto this pixel on the screen, right? So if there's something here, it's going to end up on that pixel. If there's something further behind it, it's going to end up on the same pixel, right? If there's something in this point, it's going to end up on the same pixel. But that's true anywhere. So imagine this line is just a geometric line, right? It actually goes through your eye and behind you. It's not particularly straight, what I just drew, but this is, imagine this is straight, okay? Well, if there's a point back here behind you, it also projects to that pixel on the screen. And you say, well, don't draw that one. And it's like, okay, but you have to actually make that happen, right? Because if you just draw everything in the world, then if there's some dude behind you here who's got a Molotov cocktail that's like burning, he's actually going to look like he's in front of you, but flipped inside out. There's like a weird thing that happens. And so you actually might be familiar with this from lenses. You know, if you push a lens past its focal point or something like that, if it's a concave lens, like the image will flip. I don't know what I'm talking about, but you've seen this in real life at some point if you ever played with lenses. That's kind of what happens here is, you know, if you extrapolate all these rays back behind the eye, then, you know, somebody who's standing up here, if you project him to the screen, he'll actually be upside down. Just if you trace all the rays, right? Like this ray from his head goes to his head. This ray from his feet goes to his feet. So you have to avoid that. Otherwise, you wouldn't be able to play the game. There would just be spam on the screen all the time. And the way we avoid that is we say, don't draw anything, certainly don't draw anything behind the eye, all right? Well, the problem is you can't draw anything at the eye either, because D would be 0, or D prime, D, the distance at which the thing is along the plane is 0 at the eye, and you can't divide by 0. And in fact, if you get anywhere close to dividing by 0, your math is going to be inaccurate and freak out. And so, well, what do? Well, there are various other reasons too why we tend to clip here, like at this actual plane. So we say, look, any geometry behind this plane, we don't draw anything. Probably the main reason for that is that it's the easiest, most consistent thing to do in graphics hardware. Like there are some reasons, like by way of convention, like the old OpenGL rendering convention would put a boundary on output Z coordinates that starts here, because where else is it going to start? And that's part of the reason. But yeah. But the real thing to understand here is that it would be bad to draw stuff behind you. It'll flip over. And all of us who wrote our own renderers back in the days when people still did that had plenty of this happen. This is not a rare thing. How does far clipping apply? In principle, okay, so we're skipping the idea of far clipping for now. Just imagine that you can see infinitely into the distance. In reality on computers, the numbers that we're going to store tend to have a finite range. Well, that used to be the case. Now they have ranges that can be very, very high for all practical purposes, but there might be precision issues if you try to render things super far, or your actual non-rendering part of your engine, like the game management part, just might not want to have all that data loaded. So in practice, we tend to have a limit on how far you can see, right? And that's the far clip plane. And just like, so this is called the near clip plane. Is this thing. The near clip plane is where the screen is in the virtual world. All right, and then the far clip plane is this thing out here. Okay. So that tells us how to figure out where a point is on the screen, right? Well, so let's draw our diagram again. So we've got our eye. I just always have to put something on it because it looks really ugly as just like a sphere. Okay, there's the bezel of our monitor. There's our screen. Wow, that's really not a straight line, but that's a flat screen TV that we just looted and brought home and plugged it in. And now we're able to play a wonderful video game. So let's say again we've got our building out here. And so you can see through the window. We're going to make the window bigger for illustration purposes. You can see through the window. There's someone in there looting a flat screen TV. And theirs is better than the one that we looted. They've got like the new model that does like 240 hertz with like the special motion smoothing and all that, right? So instead of talking about individual points like we were with this, let's just draw, this is like the axis along which we're looking. We're talking about objects that cover some part of our visual field. Yeah, the problem is this TV isn't actually better because it has too much latency, but you know, ignore that for now. We don't know that because we're looking at it longingly from our own place. Now I'm looking for a ruler. I know I have a ruler here. It's like I know where things are for years when I don't need them, and then one day I need them and they're not here. Let's use maybe the edge of this notebook. That's long enough. So here, instead of looking at one point, we're going to look at 2 points, right? So we've got that and, oh, whoops, I sort of, I screwed it up. I was drawing to the wrong place. Okay, that's the real vector. It's pretty close. And then for this, there. So this guy is pretty far back. You know what? Let's redraw it with better proportions. So, okay, here's my eye with a baseball cap and hair. Here's our near plane. I'm going to try. I should have just used the thing. Here's our near plane. And here's the guy looting the TV in a building, and we're gonna put it pretty close. So here's the window. Here's his other TV, right? It's got like, he hasn't unplugged it yet, so it's got like the Netflix demo showing, whatever. Somebody else is here about to take the TV from that guy because he wants it. Okay, so we're just going to talk about the top and bottom of the TV. You could think about the 4 corners of it, but we're sort of going to stay 1D here. So the bottom of the TV is here, right? And then the top of the TV, let's say this top corner, we also trace the vector from that to the eye. So we're doing this operation that we talked about on the previous page, right? This thing here where we talked about dividing by D to do these similar triangles and figure out the point on the screen. We're doing the same thing, we just do that twice, right? And we get 2 different points here. Well, that is the pixels on the screen covered by the image of the TV. And then if you knew what color the TV was, then you color all those pixels that color, and that's how you draw an object. And then if you want to draw this dude, well, he covers some pixels from like the TV to down there, right? So like that's where his feet are. And so the dude is on these pixels. And it tends to get really crammed in here, but hopefully you get the idea. All right. So well, how do we represent these things in the world, and how do we get them to the screen? Because so far what we've talked about here is just a mathematical relation that maps. It doesn't even exactly map to a pixel, right? It maps to a point in space. Now, what actually happens in video games, as you'll know, if you look at this stuff, is if I go into this editor for my game and I click on things, like all these things are made out of triangles, right? You'll know that. And like this rock here, let's maybe zoom way in. I guess it's not drawn too brightly right now, but hopefully you can see this. It's made out of a bunch of triangles that are different sizes and shapes, and they all go together to make this oddly shaped rock. And if I click on the guy here, same thing. He's just like really a lot more triangles. Hopefully you could see that. So why? Does anyone want to try to answer this question? Can anyone tell me, in video games, first of all, why do we render things to the screen using triangles? And secondly, why are things usually made out of triangles? Which is, the second one is a little bit more, you know, there are going to be people who say, nah, but yeah, mostly things are made out of triangles. Because triangles are easy to operate on. Yes, why are they easy to operate on? 3 points to make a plane. That is true. It's the simplest shape. That is true. It's flat. That is true. Triangle rasterization is faster. Not really. Triangles are always planar and less degenerate and are fast to clip. That is very true and is one of the actual reasons. Okay, there's some pretty good answers happening. Good. This is what happens when there's 1,000 people in chat. You actually get some good answers. Yes. Okay. So if you want this flat screen TV, let's make something besides a flat screen, because this is also a screen. You know, let's say, what else is something that somebody would be looting that's a really valuable, important object that is really worth ransacking all these stores? Air Jordans, a cheesecake. Yeah, a cheesecake. Okay, it's totally a cheesecake. That's what it is. All right. So, and a cheesecake is good because it's a round object. All right. All right. So, what's the best way to talk about this? Okay, so pretend all along this hasn't been a TV. This has been a fine cheesecake with cherries on top. Okay. This is the Cheesecake Factory, which is why the windows are so big. .240 Hz cheesecake with motion smoothing. Okay. There's lots of ways you could represent a cheesecake, right? If you were watching the really old movies from way back in the day, or really old rendering systems that did render with ray tracing, or you used VRML back when that was at the dawn of the web, when everyone thought the web was going to be a cyberpunk VRML paradise. You had various other ways that you would represent objects, like in ray tracers, they like their spheres, right? So you would actually have a thing that's mathematically a sphere in space. What is that? Well, it's a point and a radius, and then maybe some other properties for the surface, like what color is it? A cheesecake, you might say, well, that's a cylinder, okay? Well, you can represent a cylinder as an axis and a radius. And the axis is just 2 points. So that's not that much more complicated than a circle. So why don't we just make our cheesecake a cylinder? And the answer is, well, the answer is sort of, how do you tell the graphics processor what that is? Because the thing it needs to do is it needs to do this line intersection with the screen for everything in your scene. And that's a lot. Like on a 4K monitor, there's like at least 4,000 pixels, right? It's actually a lot. Many, many more than 4,000 pixels. It's millions of pixels. So I would go so far as to say it's over 9,000 pixels on your 4K monitor. So it has to do this a lot. And so what do we do? If you could actually have this cheesecake be a cylinder, and then every time you want to draw a pixel, you draw it forward and you say, okay, I want to draw this pixel here. Well, what's the vector from the eye to the pixel? Let's extend that into the world. Does it hit the cheesecake? Oh, it hit the cheesecake right here. What color is the cheesecake right there? Okay, so, it's kind of cream colored. So that's the color of this pixel. You can do that. That's what we call ray tracing, though, or that's part of ray tracing. And it's a little too slow to do generally. So we do instead this thing called back projection, all right? Where it's a pretty fast thing. Let's say we want to draw this cheesecake. If we just know the coordinates of this point, right, we can project that onto the screen using that similar triangles that I mentioned before. And then if we know the coordinates of this point, right, we can also project that onto the screen back here. So again, these are going to result in screen points that are a little bit close together. That's just how it is. Then if you want to draw the side of this cheesecake that you can see, once you know these 2 points, if you imagine the cheesecake is all the same color, just to simplify the situation for now, then you just figure out this coordinate and fill all the pixels between them with cheesecake color. All right. If we zoomed in, this line segment would be a lot bigger, and it would make sense why you would do this. Also, if I didn't draw this line really jagged, because this line is actually a little lower. Okay. Except, of course, this diagram that we're doing is in 2D, and we need to do this in 3D. So let's go back to, remember our first diagram, which was you just got a screen here, right? And so what we want to do is be able to fill regions of the screen. We don't want to do one pixel at a time, do this big query into the world. We want to fill regions of the screen. And I mean, we could do that any way that we want. So we could, pick a weird shape and say we're going to draw all the pixels in this shape. That's not very, that's a weird thing to decide to do, right? But what we do instead is, if you were to divide, let's say you were to divide this screen into ordered areas, that might make sense. So I don't know, maybe you draw a big rectangle at once, right? That's sort of an ordered way to approach the job of drawing the pixels in the screen. If you had objects out in your world that happened to project to the corners of this rectangle, then rendering it would be very easy because, you know, like if this is the top of the cheesecake and this is the bottom of the cheesecake, then you would get these 4 points and you would say, aha, we just fill all these pixels with cheesecake color, right? Now, on a very low-res device, that might be the case. But on a high-res device, if you have a cheesecake out there, it's going to be, you know, the person's holding it at some jaunty angle maybe, and it's not going to align with any portion of the screen in a very orderly way. So you need to come up with some way of doing this that handles a lot of arbitrary orientations, right? What if you made the cheesecake out of axis-aligned rectangles? Like if this was my model of my cheesecake, and I was going to say it's like a Tron cheesecake made out of rectangular slices like this, and then we could adjust the colors. It's like a grid cheesecake. Well, the problem with that is as soon as you rotate these, they're not axis aligned anymore. So if you're going to try to do some rendering operation that goes along rows of pixels, it's not going to make sense because these rows do not match the rows of the screen anymore. And then also, as soon as you add perspective, these aren't going to be rectangles anymore. They're going to be, you know, sort of parallelograms. They're not even parallelograms. They're just going to be like 4-pointed shapes. They're going to be quads, right? But not with any regularity that you could exploit. Quadrilaterals. So it won't even be trapezoid because I guess irregular trapezoid. I don't remember all my, whatever. Anyway, they're quadrilaterals. So that's not a very, like saying that that's how you represent your object in space is not very useful because it doesn't translate into anything that's useful for actual rendering. But here's the thing, is that if you have a triangle, just like a flat triangle in 3D space, right? Then that also projects to a triangle on the screen. So if you handle triangles in 2D, okay, so let's just say, if I say, well, as soon as I start rotating and having perspective, there's all sorts of irregularities, so I can't really be axis aligned. But if I figure out how to draw a triangle, like let's say I look at this triangle and I figure out which pixels have their centers inside the triangle, and if I figure out how to do that for this, then if I have a bunch of triangles, right, I can make shapes out of that. And those triangles, so here's where maybe we try to do a more complicated diagram again. So we're going to combine this with this, sort of, and we're going to do a 3D version of this eye with all the rays, all right? So like, here's our computer screen in the real world. We're gonna like foreshorten it because reasons. So here's my eye with the baseball cap, and so again we're like looking through this screen like we were before. But this is now like a triangular pyramid instead of just a triangle like it was in the 2D diagrams, right? So this triangular pyramid, if you extend these 4 lines out into space, tells me everything that I can see, okay? And then, you know, the looter holding the cheesecake is like back here. And let's make it a very big cheesecake again so that we have a hope of whatever, right? So it's, yeah, imagine this is a very round cheesecake for now. Okay. So let's say we make our cheesecake out of a bunch of triangles. And for the purposes of this diagram, they're going to be very large triangles. In reality, you can make this out of very small triangles and approximate a shape, right? But let's just say this part of the cheesecake, it's like a game from, it's like Lara Croft Tomb Raider from like 1994 or whatever. No, that was later. That was post-Quake, wasn't it? Anyway, they're very, very large triangles. And so what happens is if you do this projection operation that we've just been talking about on all 3 points of this triangle, then the wonderful fact of mathematics is it's still a triangle, right? A square doesn't stay a square. A circle doesn't stay a circle. I guess it projects to an ellipse, though. But building things out of circles is not very convenient. But so this is a triangle in space. And if you project it and intersect these lines with the screen, then the thing that you get is also a triangle. And so if you make things out of triangles in 3D, then the projection will also be triangles, right? And that allows you to project shapes onto the screen by projecting a smaller number of points, because you don't need, like you would in raycasting, to project every single point on the cheesecake. Let's put the cherry on top, right? So you don't need to project every point on the cheesecake. You just need to project the points at the corners of the triangles, and you can pick how many triangles you want to make the cheesecake out of, right? You project those to the screen, those make triangles on the screen, and then you just have some rule for filling in the triangle, and that lets you render very quickly. Okay, are there questions about that? Okay, guys, I didn't even realize, but this is very fortuitous. We have an extra special guest illustration. When I ordered pizza the other day, I got cheesecake on the side, and I haven't eaten it yet. So we have cheesecake, but it was delivered by Uber Eats, so it's like upside down in the box, but it's in the shape of a triangle. It's illustrating that cheesecake can be a triangle, okay? But let's extract our cheesecake from the box so that it's at least right side up. Okay, we're going to put the plate on top, and then we're going to go like that. Yay, look, it's a triangle. This is what you get when you order from Uber Eats. Okay. Okay. It is, however, very delicious cheesecake, and I paid for it. I supported the people working at the restaurant by paying for the cheesecake and for their time that they spent to create the cheesecake. Okay. So yeah, it's not a triangle anymore. That is true. Okay. A triangle could also be a line. Yes, if the triangle is edge on, if you imagine this cheesecake is rotating around, like one of the looters took the cheesecake and was getting chased by the police and fled to Cape Canaveral and got in the Dragon Endeavour spacecraft ship and got launched to the International Space Station, and the cheesecake is like floating in 0G next to the inflated dinosaur, then this triangle will be rotating over time. And once in a while, it might be edge on, right? And so if it projects to an edge on the screen, it's probably just not going to fill any pixels. But neighboring triangles will fill pixels, right? So yeah, if a triangle projects to 0 pixels, you probably just don't render anything. And well, furthermore, if you build a solid object out of triangles, like the backside of this cheesecake, like there's a surface of this cheesecake, or half of the cheesecake is facing away from the screen, right? And you can't see that at all. But like the game doesn't know that. We'll talk about this in a minute, but you end up kind of rendering those triangles anyway. But when you project them, you say, oh, they're facing away. So we don't draw those. So anything facing away from the screen or that's edge onto the screen, you don't draw. And so everything that projects at least a little bit to the screen is in fact going to be a triangle. Now, again, why triangles? I mean, you know, why don't we fill, you know, so what? So what if you project like a square or a circle and you get some other weird shape? Why don't we do that? And the answer is, in addition to just using these vertices to get positions, you can use them to do other things like interpolate colors, right? Or you know, there's this thing called texture maps in graphics, which is where you take a bitmap and put it on an object. And the way you do that is you say, well, each of these coordinates in space, or in the space of, each of these vertices of the triangle in the cheesecake have coordinates that are in a bitmap. And then when you're going to draw it on the screen, you just need to interpolate between those coordinates, and that tells you what pixel in the bitmap to put out each pixel in the screen. Like that is actually a subject. That's its own whole rabbit hole that we could go very deep down, but we won't right now. There are other things you can do. Like again, if the sun is out today, then you could say, like the way it's done this way less often today, but in the old days you would say, well, lighting is expensive to compute, so we're going to only figure out sunlight at the vertices of this object, of this triangle, and then we're going to interpolate that per pixel. So there's all sorts of ways that you interpolate things. Now, if you have something like a square, okay, this is where it gets a little complicated to explain, and I'm not necessarily inclined. I'll just give you something to think about, like if you care about this. Imagine that you made all your objects out of squares, or sometimes out of squares. This was a thing that we actually did back in the day. My first game had meshes that had squares in them, or quads, right? And the reason was it just seemed expensive to be rendering so many triangles, especially when you're writing the rasterizer yourself. So you're like, well, why not? If sometimes we know our objects have bigger planes, why not just make that out of them? And the answer is because it's not really well defined what the interior points should be. So even before you think about projecting to the screen, all right, let's say we have two cases, a triangle and a quad, and then we're going to we'll make a third case out of both of these. So let's say this is red, this is white, and this is blue, right? We decide that each corner is a different color, and that's how we're representing the object. Then mathematically, you can blend these three things together consistently, and it's called Barecentric Interpolation. And so you know for every point on this triangle what color it should be. Again, that's a whole rat hole we could get into. We're not gonna, especially because there's probably a very elegant explanation that I could give of why this is true if I had prepared it, and I haven't. And so it might end up being a rambling explanation where we could do it in like 3 minutes. I'm sure somebody on YouTube explains this very well. Okay, well, for quads, you could project all 4 of the points, right? But the problem is, like, what if this is like white, red, blue, and I don't know, purple or something, right? And furthermore, what if you look at this quad edge on, and it doesn't even fit a plane, which is guaranteed to be true due to numerical accuracy, by the way. But imagine you didn't even care about that. So this triangle, 3 points are always on the same plane. So you know what the interior coordinates are of any point, right? For this quad, if you were to look, okay, if you look at a triangle sideways, you're always going to see, you can always find a place where you're looking edge on and you see 3 points, right? For a square, that's not true if these points are not coplanar, because 3 points determine a plane. So imagine you have a quad where these 3 points are on a plane, but this one is actually some elevation off that plane, right? Then there's not even a way to know where in space the interior points of this quad are even supposed to be, right? So like if you looked at this edge on the way that we're looking at this triangle, you might end up with like one, like maybe this is the red point and this is the white point and this is the blue point, and then like this is the purple point, and then like you sort of know, like there's no, you can't actually ever get it edge on, because if you line it up by these 3 points, this sticks up, right? And if you line it up by these 3 points, this like sticks down, or like that. So you can't actually, it's like a weird ill-defined thing. And so you have to decide, well, if I even wanted to know where these interior points were in space or what color they are, you have to decide essentially what plane they're on in order to do the interpolation. And so you end up anyway either splitting this rectangle this way, and then you say, okay, well, this plane is well-defined and this plane is well-defined, or you split it along this other diagonal, or you do something else more complicated. So you end up turning the plane into triangles in order to have a mathematically well-defined way to know what's in the interior of the rectangle. And that's true for any more complicated shape, right? So the reason we use triangles in part is because 3 points determine a plane. And so as an approximation to an object that's in 3D space, right, you want to know what are the points of that plane everywhere, both in real geometric space and in color space and in texture map space and all these things. And so that is well defined for a triangle. It is not well defined for something like a quad. You can make very complicated primitives for which it is well defined, you know, when you provide enough parameters, right? I mean, you can provide enough parameters to this quad. It's just not that interesting. You could have like, I don't know, NURBS or some kind of spline thing, or other spline thing than NURBS, I mean, or there's like lots of different ways that you could specify things, but they're not easy to render. And so triangles are the thing that we know how to render fast, that is also well defined. Okay, so are there any questions about that? Is it a bad idea to switch primary topology to line if you want to render a line? The secret is when you say to render a line, your GPU renders 2 triangles, actually, probably. What do I mean by well-defined? I mean that, let's say, I realized I was rambling a little bit in the middle of that. Sorry. Okay, let's say we have 3 points for a triangle, and they've got coordinates. We're just going to talk about coordinates in 3D space. One thing that might have made this confusing was I started talking about colors and then I switched to coordinates and then texture maps and whatever. So let's say this has coordinates. x1, y1, z1, x2, y2, z2, right? x3, y3, z3. If we were feeling really crazy today, we could go into like what are coordinates anyway and what do they mean and why. But we've got to cap it off somewhere and make forward progress. So we're not going to do that. Okay. So let's say you've got this, and let's say I ask you, at this point, let's say you know the coordinates of these on the screen because you did that similar triangle projection thing that I said before, which is actually the triangle in similar triangle is different from this triangle that we're drawing, which might be a little bit confusing, but maybe that just tells you how useful triangles are, that they come up multiple times. Okay, if I ask you, what are the coordinates of this point in space given the coordinates of these 3 points? And how do I specify this? I kind of don't. I see it becomes a tautology if I say you specify it barometrically. Let's imagine let's imagine that this is axis aligned, like this is the bottom of the screen, and we have, I don't know, some right angle here, and we're saying it's this distance along the triangle and this distance in, right? So I specify some point, and I ask you, what are the coordinates of this point? And we're not going to go super much into interpolation right now, but the fact is that this is well defined, all right? Because like I said, these points determine a plane, and so as long as your assumption is that everything between those points is a plane, right? That's like the thing that makes this work is you say, my object actually is a plane in between these points. Then you can find the coordinates of any intermediate place on that plane for anywhere here. If I give you that for a quad or anything else, well, not anything else, but let's say a quad. The problem is a quad is overspecified. So let's do the same thing. I don't know. It's like it's a funky quad with no particular regularities. Whoops. X1, Y1, Z1, X2, Y2, Z2, right? X3, Y3, Z3, X4, Y4, Z4. If I ask you, okay, we're doing a similar thing where we have a point here. What are the, I really didn't draw that as a right angle, but like, what are the coordinates of this point in space? You can't actually answer that question with the information given, because it's ill-defined, because this quad defines at least 2 different planes, because so these 3 points determine a plane, right? These 3 points determine a plane. These 3 points determine a plane, and there's 4 different planes here. Okay, sort of. And there's not really enough information to say which one. And then by the time you provide information to say which one, it's like not a very good representation. Like you might as well have just made triangles out of this. Okay. So we can't explain that in more detail without going mathematically into like, here's the plane equation and here's how you compute it from 3 points and blah, blah, blah. We're not going to do that. But that's the actual answer. More than 4 points creates more than one plane? No, 4 or more points creates more than one plane. Okay. Is there some notable way hardware accelerates the triangle raster? Yeah, there's a bunch of things. We're actually not going to go into that either because it's a big topic. That is also, I'm not a GPU engineer, so there's lots of stuff there that I don't know. Could you have bigger polygons by specifying a plane and then more than 3 points with 2D coordinates in plane space? Yes, but that's not that useful of a of a representation. Okay, so if you start talking about having more complicated primitives, then you start making your life harder in various ways. Like I have to store those things, and I have to be able to operate on those things. Like let's say I have this cheesecake, right? And it looks too tall, so I want to stretch the cheesecake this way. Just in game, like we're not even talking about rendering it, but in the world, I want the cheesecake to get wider, okay? So you can do that. If it's triangles, you know that your representation is essentially just a bunch of points. You have a list of points that are basically, let's zoom in on this again. So I have my very thin cheesecake and I want to make it wider, okay? And so I'm representing this cheesecake as a bunch of points, first of all. I'm just going to draw points, right? And then, well, it's triangles between the points. And how does that go? Well, you know, like this. I don't know if I want to draw all the triangles, but you get the idea. This is how, this probably would be a very messily modeled cheesecake, but there you go. So, and then this would be a line segment, right? Because we're approximating the cheesecake with triangles. So now, why do we do this? And why is, well, we already talked about the mathematical thing, but you could, as long as you can answer that mathematical question, then other representations are okay. So why are we using this one? Well, if we wanted to make the cheesecake, we want it to have a bigger radius, say. Well, we have this list of points. So array of points and array of triangle indices, right? So how does this work? Is like, okay, this is point 1, this is point 2, this is point 3, point 4, point 5, point 6, 7, 8, 9, 10, 11, 12, whatever. Each of these points has a unique number, all right? And then this array of points is the following. Point number 1, point number 2, point 3, point 4. It's got some memory for each of these, right? And then what's in there is just the coordinates of each point. So this is like x1, y1, z1. And this is x2, y2, z2, right? Where these are just those coordinates in space that we were talking about here, all right? So, this is x3, x4, Okay, this array of triangle indices, which we're going to have to draw down here, there are ways of compressing this and making it more compact, but, okay. Let's add 2 more variables. Let's say let n is the number of vertices in the cheesecake, right? Okay, and let's say let t is number of triangles in the cheesecake. Okay, so then there are n of these. It goes 1, 2, 3, 4, all the way to n, right? And then for the triangle indices, it's a different array. It goes 1, 2, 3, 4, all the way to t. Now each of these up here, this is n times 3 floats, right? So a float is a way of representing a real number. N is how many vertices there are, and there's 3 coordinates per vertex. So this is an array of n times 3 floats, all right? That's the points. And then the triangles is, it's an array of t times 3 integers. And what are the integers? They're just what number is each triangle. So here we have a bunch of triangles. These numbers don't really correspond to these. These are just array indices. We could be C style and start at 0 if we want. Okay. And if we just, let's say we just start talking about all the triangles in this cheesecake. So this is 1, 2, 3 right here, right? We're going to color that in and say we got that one. So that's 1, 2, 3. Here's another 1, 2, 3, 4, right? So we're going to color that in. So far, these are in a nice order. But this one is 2, 4, 5, right? 2, 4, 5. This one is 4, 10, 4, 11, 10. We're doing these counterclockwise, which is a way that you tend to... Remember when I was saying we don't draw things if they face away from the camera? The way you know that is by establishing a convention that, for example, counterclockwise orientation means facing outward. We don't need to go too much into that to establish the basic idea. So this is 4, 11, 10. 4, 11, 10. This one is going to be 1, 12, 11. We skipped this one, I guess, but whatever. There's a hole in our cheesecake, just like games from the 90s. So if you do this process for every triangle around the surface of the cheesecake, you now have a way to represent the entire object. And this is a way that's easy to manipulate, and that's important, right? So if I want to increase the radius of this cheesecake, I don't have to touch this list of triangles at all, because the triangles are not going to rearrange if I resize the cheesecake. All that I need to do is move the spatial coordinates. So I just do a little bit of math that says, well, if I want to increase the radius of the cheesecake, then there's some axis here along the middle of it, and just take the vector from that axis to each point, and then scale that by like 1.5, and that's the position of the new. So if this was old 0.7, this is new 0.7, 7 prime or whatever, right? If this was old 0.2, this is new 0.2, 2 prime. And so you can define operations that you could do on the cheesecake pretty well, as long as you know what's going on. Does that make sense to people? Any questions about that? Make sense? Make sense? If you use a triangle strip, you don't need the triangle index less. That is true. There's things like triangle strips and triangle fans, which are just ways of representing this with fewer numbers. Because, for example, here, you see this like 1, 2, 3, 2, 3, 4, 2, 4, 5. That's a pattern, right? And anytime you see patterns, you can exploit those patterns to represent data smaller. And so the problem then is it gets a little more complicated, because it's like, well, we broke the pattern here. So we sort of have this easy pattern and then not. And so you can end up with a smaller representation, but it's a little bit more complicated. Okay. So actual games tend to have objects with like multiple of these per object. So let's go back to the game here for a second. Let me see. We're going to go into our little palette world here. Let's sort of go. So you see here's a character standing in a T-pose, and she's got like this metallic armor kind of stuff, and then like a cloth cape and hair and all these things, right? And the way that graphics processors work is we're doing different stuff to each of these. Or, there's a thing called a shader that draws all the pixels for each of these. And even if we use the same shader for these two things, which I don't think we do right now, I'm not actually 100% sure. Wow, the camera frame rate is kind of dying. We're going to close the game here in a minute because it's not good. Anyway, so even if even if it's the same shader, you need to specify how these should be rendered. And they look so different. You need different data for each of them. So we tend to do it in 2 different passes, right? So we do triangles that are gold armor triangles, and then we do triangles that are cloth cape triangles, and then, I don't know, whatever, the hair triangles. They're different materials. So each one of those materials will be, yeah, my computer's choking when I try to do too much of this. Each one of those materials will be, you know, a set of these coordinates and a set of these indices, and then some extra information like, you know, bitmap and, you know, there tend to be some numbers that define a material, such as like albedo, which is how much light bounces off the material. Maybe there's a base color like scale color that you're multiplying things by, you know, specularity or other reflectance. And there are different models of how shaders work that give you different numbers like this to tweak. And anyway, so the way you organize your mesh is by a set of these batches. We can call them batches for now, where a batch is some triangles and some coordinates and some material properties. And, you know, maybe there's other per vertex properties. So like if we have a bitmap here, we need to say where in each bitmap every one of these vertices is. So in addition to having spatial coordinates here for each one of these, we might have like also U1 and V1, U2 and V2, U3, V3, where those are coordinates in some other space that defines the bitmap, all right? But the good thing about this is whatever you add here, it's a very compact, uniform representation. It's very easy to deal with. Right? So this is why we've been doing it the same way for 25 years. There's a lot of things that we've changed about how games work. There's a lot of things that that we've gotten better at, that we've learned how to do. Like we didn't really know how to rotate objects 25 years ago very well. Or at least it was understood only by very few people. But this has been basically the same idea ever since we started having 3D rendering. So now, the way that the computer works today, back when I started, when you were going to go do this whole process of figuring out what color every pixel should be, based on this whole thing that we've explained about projecting the triangles and all that stuff. This used to just be your program doing all of it. You would write the program that goes line by line over the screen or in whatever other pattern. And for every line, for every pixel, you like do a thing, right? Okay. And that would involve, you know, a lot of optimization around how do you project the triangles quickly? How do you interpolate scan lines? Like a renderer that I wrote one time, which was based very heavily on the stuff that Mike Abrash was publishing, and then Chris Hecker also was publishing some stuff that I sourced. You know, you would step line by line down the screen, and you would have like an active triangle. Let's go into that for a second, because it'll take some of the mystery out of it. I don't have to just say, and then magic happens and you have pixels. So once you've got a triangle that you projected to the screen by the methods that we were saying before, let's say our screen is this whole sheet of graph paper, right? And these squares are just pixels. So I've got a triangle, and I've got some other stuff like colors and texture maps and whatever, and I want to draw this actually on the screen. Well, back when I started, what we did was you said, well, okay, the triangle starts at this pixel. Now let's render this scan line. We would walk down the screen and say, okay, this left edge of this triangle has, you know, you learned from grade school, hopefully, that there's different ways to talk about a line. You have this like y equals mx plus b that we learn. But there's another way of, doesn't matter. You know, there's ax plus by plus c is 0, which is much preferred. Y equals mx plus b is kind of trash. You shouldn't ever use this as your fundamental line representation. I wish they wouldn't teach it in school. This is a line in 2D, like really. And from this, like you can see very easily that so x and y are our screen coordinates, right? So if a goes up, x goes up, and if b goes up, y goes up, right? So so you can figure out for each pixel of y, right? How far do you go horizontally, right? And I think it's just a over b. I'm just going to claim it's a over b, whatever. If I mess that up slightly, it doesn't matter. But in principle, you say for each pixel that you're going to walk, this left edge goes, let's say minus 1.3 pixels, right? And this right edge goes to the right by like plus 0.157 pixel, whatever. And it would be expensive to do this in floating point numbers. We didn't do that back in the day, but that's essentially what you're doing. And so if you know, so this is y0, let's say, right? You know that the extent of the left edge of the triangle and the right edge of the triangle are both just whatever the coordinates were that you projected. Let's call this x0 and x1. These are different. Okay, these x's are different from these x's that we talked about over here. Different. These are screen coordinates. Okay, so what you say is, okay, if you know dx, dy, this is a little bit of calculus language, but if you know dx, dy for left edge, right, and you know dx, dy for right edge, which is just, since these are going to be called x0, x1, this is dx0 dy and dx1 dy. If you know those two things, then you can just step down the screen. And for every scan line that you go down, every time you add 1 to y, then you add dx0 dy to x0, and you add dx1 dy to x1. And so you can compute the edge of each triangle, right, in the following way. Like you make a loop, like while 1, we're suddenly in pseudocode land here. While 1, we'll put parentheses in case it's C or something. So y plus equals 1, let's say plus equals 1. I don't like left-handed coordinate systems, which is what you get if y plus equals 1, but I said dy dx is like positive, so whatever. This is what we're doing. And then x0 plus equals dx0 dy. This is C, so like we're not writing fractions, right? And then x1 plus equals dx1 dy. And that gives you these two pieces. And then what do? Just say like fill pixels, whatever you're going to do. Let's just say we're going to fill pixels makes it a solid color, right? So you just do this. You're going to have to break eventually, right? If something break, otherwise this is an infinite loop. But so every time you step 1 pixel in y, you know how much to adjust these x coordinates, and it's constant because these are lines, okay? This is again important. This triangle is valuable for us engineering-wise, not only because it defines a plane in space, but the edges of it are lines, and a line means that these dx0 dy and dx1 dy are constant. So we step the same amount every pixel, okay? So you just go, and you step, and step, and step, and let's just say we're way down here now. We've done every line in order. When we get here, we have an x0 that represents this, an x1 that represents this, and we fill that with a solid color or interpolated across a texture map or whatever, right? Now, this doesn't get you the whole triangle, Because the problem is, when you hit this vertex down here, suddenly things have to change. So your x1, your dx1 dy is still the same because this is the same edge. But because you hit this vertex, now you have to change dx0 dy. Needs to get recomputed, right? So you actually draw one triangle sort of as two triangles because of this switching point. So this used to be minus 1.3. Let's put that over here. And now it's like plus 1.5 or something. It's changed direction. And then eventually you get down here. And when you get down here, you're done with that triangle. And so this break over here where we said if something break, this would be if you get to this line, break. And then you have another loop that says, okay, go from this line to the bottom. Does that make sense to people? This actually tells you, this is cool. I didn't know that we were going to rat hole this far, but we've talked about how you go all the way from the abstract idea of objects in space, right? How you represent them in memory, and then how you can put them on screen as pixels. Good so far? On-topic questions. Are there any on-topic questions? Because this has been a long explanation, and it's time to get to sort of the point. Is this how modern GPUs actually do it? Kind of, but not really. GPUs don't really go in long scan lines like this, both for reasons of memory locality and also in order to be able to parallelize better. So they tend to do operate on blocks of pixels at a time. And different GPUs will have different implementation details. They don't tend to go top to bottom, left to right, or whatever. That's not a thing. Are we going to talk about anti-aliasing? No. Okay, so now let's start getting to the actual problem that we covered at the beginning with the game not being that good. So this representation of a mesh as a couple of arrays is very efficient, right? So not only is this easy to manipulate, like if we want to change the size of the cheesecake, so it'll be too big for the looter to carry unless she goes and works out. It also, well, the way that we treat meshes in games is that they mostly don't change, right? If you're carrying this cheesecake around, it's the same shape. We know how to rotate it, right? But we don't have to change the shape to rotate it. You might have like a destructible environment with deformable cheesecake, but that's sort of a special exception. You know, usually it doesn't change. And that's good because here's the problem that we have now is in our computer, you have the CPU, which is running most of your game actually, right? And then you have the GPU, which draws real fast. And the problem is the CPU needs to talk to the GPU essentially over the telephone. But it's like, you know the game where you have like a can with like string and it goes to another can with string? It's like that, except the string actually goes around the universe and eventually gets to the GPU. And there's like other strings and there's like a switchboard, whatever. And then like there's maybe a looter with a Molotov cocktail over here that might burn the string. This is like when your GPU driver, I mean, basically the dude with the Molotov cocktail is your GPU driver. So anyway, so you don't want to talk to the GPU that much if you want to be fast, right? And actually this situation is better on game consoles. So if you have a PlayStation 5, it's not this crazy. On a PlayStation 5, it's just more like that instead of this whole giant thing with the Molotov cocktail. So So you still, though, don't want to talk to the GPU that much. So what you do is when your game starts up, it hands the cheesecake to the GPU, right? So you're saying, here's the cheesecake with the cherry on top, right? And what does that mean? You're uploading some data. Remember how we had our array of indices of the triangles, an array of vertex coordinates, and other stuff like material properties, right? What happens is you allocate some memory on the GPU. Let's say this box represents all the memory. You allocate some memory on the GPU, and the cheesecake lives in that memory. Here's one array, and here's the other array. So then, when you want to draw the cheesecake every frame, you just say, hey, GPU, remember that cheesecake that I told you about? I'm not going to tell you all the vertices and indices again, because that's expensive. Just remember those. And I'm just going to say, here's the position of the cheesecake in space. So I'm going to tell you about the position. I'm going to tell you about the orientation, like how is it rotated? Maybe the scale, maybe the lighting on it. You know, whatever other tweakable shader parameters, I'm going to tell you those. And let's just say object ID of the thing that we're actually rendering. So this is the data that gets sent over the wire. Oh, also like shader, like what shader are we going to use to draw these things? That information goes over the wire, and you don't actually say the shader, you like set up the shader, whatever. But basic idea is most of the data lives on the GPU, and then you send a small amount of data when you want to draw the cheesecake on the screen. And the GPU runs your shader that you wrote and uses this information to do this projection, so it uses this data and these arrays here that we talked about to do this thing, this similar triangle operation for every triangle in the cheesecake. Where's our 2D, 3D cheesecake? Oh, here. For every triangle in the cheesecake, it does this to get a projected triangle. For every projected triangle, it does something like this rasterization operation, but different. And then in the end, you're able to draw that whole cheesecake without sending very much data every frame. And that is why video games, when they're programmed well, actually run very fast, even though they're drawing a huge amount of stuff. Because we've designed, this GPU is very, very good at rendering pixels. The CPU is, good at other things. It's actually pretty good at rendering pixels, but the GPU is way better at rendering pixels. The CPU is like some guy who's like in middle school or high school and went to karate class a couple times a week, right? And then, the GPU is like the kid who grew up in China and his dad made him go work out at the Shaolin Temple every day for years. And this guy thinks he knows karate and whatever. So sometimes analogies don't go anywhere productive. So that's how we render things. So the way that we end up as a game is your game treats a cheesecake as sort of a logical unit that it talks about. Like the game, you could say, reifies the cheesecake as a concept, right? And so you have an entity, let's say, you have an entity in your game code that's the mesh is cheesecake 3 dot, let's just say it's a mesh file somewhere, right? And it's got, a position, orientation, scale, maybe it's got some additional stuff like, position in collision grid, whatever. there tends to be a lot of administrative data. So your game engine is keeping around data. Remember how we said there's like an object ID? You might associate that with your storage of the mesh in the game engine. So rendering object ID. Object ID. So this is the thing. This and this and this and this are the things that we would pass when we want to draw the cheesecake on the screen. Those are stored somewhere in memory. And so here we're finally talking about like the gameplay code. All right. Now, of course, if you're an impressionable young indie these days, you look at this and you think, oh, that means I have to have an entity component system in Copy Unity. And you make your thing way too complicated and never finish your game, and it doesn't work very well. But you don't have to do that. You could just store this data straightforwardly and then pass it to the renderer when it's time to draw the cheesecake. Okay, so, well, we want to be fast, right? Games are like Sonic. They got to go fast. What does that mean? It means when it's time to render a lot of cheesecakes, or like if you want to render the whole cheesecake factory, right? You've got several cheesecakes. You've got like, I don't even know what they have at Cheesecake Factory. Don't they have like hamburgers and stuff? You've got like a hamburger. You've got like some plates and some tables and forks and whatever all these things are that you want to draw on the screen. The gameplay code has probably, maybe not, but possibly an entity for each of these things. And it says, hey, GPU, draw this cheesecake. Hey, GPU, draw that cheesecake. Hey, draw this fork. Draw this bottle of beer, like whatever, right? And I told you about that bottle of beer before. You better remember because I'm asking you now to render it, and this is a test, right? So the game does that. The game wants to talk about these things at a very high level, and it wants to be computationally fast, okay? Now, problems can arise. Like, for example, if you just do the very naive thing that I said here about how to rasterize, every time, let's just say every time I draw an object, we're going to do the coordinates like we said. We do all these things. We do these things. We figure out the triangles. We rasterize the triangles. And we do this and we fill the pixels. Okay? That is not enough. Because what happens, so first, the game is going to say, here's a cheesecake. Please draw this. And so we draw it. Again, this graph paper is our whole screen. So we draw this cheesecake. With a cherry. This is very bad perspective, whatever. We draw this cheesecake, and then we say, okay, this cheesecake is being carried by a rioter. The rioter is holding, that's not a very big head. I guess rioters have small heads. There's a rioter back here, and the rioter is holding the cheesecake. And this is going to be hard to draw, especially with a stick figure, but like, their hand is back here. And again, so the GPU is good at rendering. The CPU, it just wants to say what to render, okay? And so, so then I say, well, there's a hand back here holding the cheesecake, right? If you're triggered by me saying that it's a riot or just, you know, it's a party. It's like a laugh riot party. You know how that's a positive, like, oh, your party was such a riot. So the people at the party are rioters. So, so there's a hand behind this. And so now I'm going to say, okay, I say first draw the cheesecake, then draw the hand. All right. And the problem is, the CPU doesn't necessarily know which order to tell you to draw these things in. And so if I tell you to draw the hand second, you're just going to do all these steps that I said. Okay? You're just going to do all these steps that I said and draw the hand, and this hand is going to end up in front of the cheesecake, even though it's physically behind. And it's going to be, okay, the arms, these are scrawny rioter arms, right? Like this rioter does not work out at all. I obviously don't work out when it comes to drawing because I can't draw anything. So you have to solve this somehow. Now you might say, well, why doesn't the CPU just figure out that the rioter is behind the cheesecake, right? And the problem is, well, what if most of the hand is behind the cheesecake, but the rioter has a big beefy thumb that's in front of the cheesecake? There's no particular order in which to draw that hand, where you draw the back of the hand first and then the cheesecake and then the front of the hand, right? So then you say, well, maybe the thumb is a separate thing. Maybe you could make the rioter out of convex pieces, like each finger is sort of a separate piece and each arm is a separate piece. And so then you can't actually end up in this situation where one convex piece is both behind and in front of the cheesecake. That's mathematically not possible. But then you end up with a problem like this. Like say one of the rioters got drunk and knocked over all the beer bottles. You can end up in a thing where you have 3 beer bottles, for example. I don't drink beer, so I don't really know what beer bottles look like. I already screwed up. So here's one beer bottle. Here's a second one that's kind of going in front of that one. This is kind of a melted beer bottle, I guess, because somebody left the oven on while they were looting. I don't know. This is beer bottle number 2. And then beer bottle number 3 goes like in front of this one, but behind the other one. All right. If you do this, if this ends up in your scene, so I'm going to dot this, right? If this ends up in your scene, there is no order in which you could draw these 3 beer bottles that's actually correct, right? Because every one of them is in front of one bottle and behind the other bottle. And old games used to have rendering artifacts like this, including games that I worked on, because you would try your best to like sort the beer bottles and figure out which one's in back. And, that's very slow and it still has problems, right? Rioter just means Riot Games employee. That's a good point. Okay, so you might say, well, okay, if you want to get scenes like this correct, well, the beer bottles are just made out of triangles, like we said, right? So why not just sort the triangles individually? So like this beer bottle is made out of triangles and this one's made out of triangles. So draw the triangles on this one that are behind, and then draw these triangles, and then draw these triangles, right? And so there are 2 problems with that. One is now it's like a lot slower because your CPU is doing a lot of work to sort all these triangles, and it used to be able to say, dude, just draw the cheesecake, right? Now it can't do that. It has to like say, draw this part of this beer bottle, and then this other part, and then that part. And that's eliminating this benefit that we would have by treating these as bulk objects with large arrays of data. Okay, that's part 1. Problem number 2 is, what if your beer bottle, it's going to be hard for me to draw this in a reasonable way, but like, what if this beer bottle, if I'm going to draw this weird misshapen beer bottle separately again, this is just like a zoom in on this one. What if it happens to be triangulated like this, right? What if all these beer bottles have these really long, thin triangles? Okay. This is not very triangular looking, but you get the point. Then splitting by triangles wouldn't even help you, because you'd have long, thin triangles on this guy, and one single triangle could be behind or in front of this bottle and behind this bottle, and one triangle of this one could be in front of this bottle and behind this bottle. So splitting up to triangles doesn't solve anything, because you could still have individual triangles that there's no way to sort them. All right? So the graphics community invented this thing called a Z-buffer. What is a Z-buffer? It is simply the following thing. When you're going to rasterize your triangle into individual pixels, I'll draw points here to emphasize. This is what we're doing, is we're putting a color for each of these points on the screen, right? Okay. In addition to storing the color, also just store how far away from the camera that this piece of the surface was. Remember, because this triangle defines a plane in space, it's well defined what point in space each of these is at, right? So it's well defined how far away from the camera each of these is at. You just do a little bit more interpolation than we did in our loop here. All right. So you just store that value. And then, so you did do this when you did the cheesecake or the beer bottle. And then when you come along and render another beer bottle or the rioter hand or whatever, as you're drawing the triangle out, you say, okay, here's the Z value. Is there something there already? Did we already draw a pixel on this screen? If we did, if we didn't already draw a pixel on the screen, then it's fine. Just draw the new one. There's nothing in front of us, right? If there is a pixel on the screen already, is its Z value closer to the camera than the thing that we want to draw? If it is, don't draw our thing because it's like our part of the hand that's behind the cheesecake, or it's the part of the bottle that's behind another bottle. Don't draw that, right? And so then you get a pixel accurate sorting of your objects. The CPU doesn't have to worry about sorting them. The CPU just says, draw cheesecake, draw bottle, you know, draw fork. The GPU does this per pixel sorting, right? And that's how we're able to render very fast. Does that make sense to people? Should I go into more depth on that in any way, or what? Wouldn't this be very memory heavy? Maybe, but it's just one number per pixel, and colors are already at least 3 numbers per pixel, so it's not that bad. I mean, it might need to be a high precision number per pixel, but this was so obviously the right way to do it from way back in the early days that GPUs specialized at this and got really good at it. Does the GPU do the Z-buffer calculation for us? Yes. In the same way that it's doing all this rasterization for us, it does the Z-buffer for us. What about transparency? We're getting there. That's the whole point of all of this that we've been doing for 2 hours, is transparency. So you render each object separately, but onto the same pixel buffer and check if your thing is closer. Yeah, the GPU does math per pixel to see if a thing is closer or not. Isn't it expensive to discard all the rendering done up to the rasterization? Is occlusion culling cheaper? Well, this is, if you can occlusion cull an entire object, you often should, yes. But sometimes that becomes so expensive that you don't want to do it. Also, GPUs, it's not, okay, so what I said is a little bit of an oversimplification, because it's not like GPUs have to do all this computation to render the pixel and then test the Z value and then throw it away, right? They could look at the Z value before they start doing the computation and say, do we even need to do this computation? I mean, you need to do enough computation to know a bound on the Z value. And you might even be able to early out. So imagine, for example, that GPU is rasterized just like this triangle that I drew, the way we all used to do it in software, which they don't. But imagine they did. So as you're tracing out the x0 and x1 for this edge, right? So remember, we were doing dx0 dy and dx1 dy, right? So you also would have a dz dy for each side, right? So you might have z0 and z1, right? And you'd have derivatives for each of those. So for each span, like this one here, you have an x0 and a z0. And on the right side, you have an x1 and a z1, all right? Any pixel in between these two edges of the triangle has a z value that's between z0 and z1, right? So whichever one of these numbers is less, whichever one of these numbers is closest to the camera, tells you how close any of this could be to the camera, right? So if for every pixel, let's just say z0 happened to be less, it could be that z1 was less, but let's just say z0 is closer to the camera. Then when we go to each pixel, we just check, is there a z value there already? is it less than Z0? If it is, we don't have to draw anything. We can early out, right? And then you could imagine doing that for whole regions of the screen, right? So GPUs don't do exactly that, but if you understand this concept, you can understand what GPUs do. How about Z-fighting? Z-fighting is an issue that happens. It's a failure of this comparison mechanism that I was talking about. If you imagine that you render two triangles that are basically on top of each other, but let's say they're not mathematically exactly on top of each other. There's like two sets of coordinates that are really close. Then when you're doing this comparison to see which one is in front, you might be subject to very small numerical error in the calculations. Like if this, imagine this is being done in floating point and you're walking two different interpolators at two different times to compare. You might end up in a point where you make the comparison different ways every frame for individual pixels. And that's where Z-fighting comes from. It's the numbers are really close such that very, very tiny numerical rounding differences are causing different results every frame. Okay, so now we're getting back, for those of you who've been here the whole time, we're getting back to the original point. Okay, this Z-buffering is a very valuable technique, not only by itself, but it enables this whole pipeline, right? It enables this whole pipeline where we represent our cheesecakes and beer bottles and forks and rioters and lice in the rioter's hair, and all the different things in our scene. We represent them in these compact ways as just a couple of arrays of very tightly packed data, right? We tell the GPU about that data in advance. We say, hey, GPU, there's 3,700 lice in this guy's hair, and here's the geometry for the louse body, right? Here's the geometry for the cheesecake. And then every time we want to render the scene, we just say, draw the cheesecake, draw the beer bottle, draw the Molotov cocktail, and there we go. So because we have Z-buffering, that enables us to do all that stuff. However, there are cases in which Z-buffering doesn't work. And one of those is transparent objects or translucent objects, all right? So let's say, what's a good example of a translucent object? I mean, we could say like a beer bottle. Let's say it's a beer bottle. It's empty of liquid because I don't want to get into like moving liquids or anything, but it's like a good smoky colored beer bottle, right? So come on, pen, don't die on me. Let's try a different one. So this is going to be like the inside of the beer bottle, and it goes up, and it goes up, and then see, I'm putting more effort in to this beer bottle. So this is a good beer bottle. It is not opaque, but it's kind of smoky colored, which I'm going to just draw some lines on it to sort of represent that. So, if our cheesecake is sitting behind the beer bottle, partially, so this part of the cheesecake's in front, right? And then it goes behind the beer bottle. You should be able to see the cheesecake through the bottle, right? Or in the case of the game that I showed at the beginning, the surface of the water is transparent. You want to be able to see the surface of the water, but you want to be able to see what's inside, right? So here, you want to be able to see the beer bottle, but you also want to be able to see the cheesecake behind it, right? Now, the problem here is, what happens if you draw these in a different order, right? If you draw the cheesecake first and then the bottle, okay, we need to do another segue. and talk about how translucency happens, all right? And it's very simple. There's this thing called alpha blending, which sounds complicated because it uses a Greek letter. But it's actually a very simple idea. All right. So let's say we have a brown bottle, right? And it's in front of a cream-colored cheesecake, right? And we want to draw these, in order. Or let's just for now, just say order is not an issue, for example, right? So we draw the cheesecake first. That cheesecake goes, we're going to zoom in. This is a pixel right here, okay? And it's cream-colored. C-R-E-A-M. What is cream color? It's a few numbers, right? Let's say it's in RGB color. Let's say it's 0.9, 0.83, 0.8. I have no idea. That's not going to be a very good cream, but let's just say it's just three numbers like that. Let's just say there are three numbers between 0 and 1. Okay? Now, I want to, because there's a brown bottle that I want to draw in front, I basically want to make the cream more brown. Okay? Let's just say, if the brown bottle were completely opaque, if you couldn't see through it at all, then when we do this rasterization process, we would just stomp the old color with the new color, okay? What's the new color? If we just stomp the entire pixel with the new color for brown, in RGB, this is like, I don't know, like 0.4, 0.15, 0.17, I don't even know. Some color, it's a lot darker than this one, okay? So if this is opaque, we just stomp all these colors in the cream pixel with the colors in the brown pixel. What if it's a little bit see-through? Well, maybe you just want it to be almost brown, but a little bit cream, right? What if it's very, very lightly colored bottle and it's almost completely transparent? Then you want it to be mostly cream and a little bit brown, right? And so what you do is you interpolate between these two colors to do transparent objects, right? And that's a very simple mathematical thing. So let's take the red channel of the color, right? So the red channel of cream is 0.9, and the red channel of brown is 0.4. Well, how do you go between those? It's pretty obvious, right? Let's say you want halfway between. Like the difference between these is 0.5, right? 0.9 minus 0.4 equals 0.5. If you want to go halfway, well, you could go halfway, right? So you could go 0.65 is right in the middle. You could go between 0.65 and 0.9, whatever, right? So we have this function called lerp, right? By A and B by some parameter t, where A and B might be these colors, right? Lerp is A plus B minus A times t, or you could factor that differently. But basically, when t is 0, you get A. When t is 1, you get A plus B minus A, which is B. And when t is in the middle, you get some blend between A and B, right? And it's a linear blend, and you start getting into nuances eventually of like, what do these numbers actually mean? Are they like linear to the number of photons, or are they like linear to, the way that your monitor wants to represent pixels in its memory, right? So that's where gamma correction comes from, right? We're not going to get into that right now because we don't need to talk about it. But what this interpolation actually does in terms of like what 0.65 actually means depends on if you're talking about photons or perceptual brightness, right? It's a different thing. Okay, so when you draw the beer bottle in front of the cheesecake, you have this alpha parameter, right? So alpha alpha is actually this same t here that you pass to the lerp, right? So if alpha is 0, the object actually won't show up at all. If alpha is 1, it will. And alpha tells you, like if you imagine there's this whole range between cream and brown, alpha lets you control where in this range you're going to be. And you apply the same alpha, right? So you do the same thing that we just drew for green and blue, etc. Right? You do the same operation on all three colors, and that's how you render see-through things. But we just said that the CPU doesn't want to draw things in order. All right? The CPU wants to just throw a bunch of objects at the GPU and let the GPU take care of it with the Z buffering. So what happens if we're going to draw this see-through bottle in front of the cheesecake, but we draw the bottle first, right? If we drew the cheesecake first, then we have a color in the background to blend against and mix into brown, right? If the bottle is first, we've already rendered this bottle and we come by to render the cheesecake. If we use Z buffering, then you're not going to be able to see the cheesecake through the bottle because we already recorded that these pixels have a Z value that's closer than the cheesecake. So we're just not going to draw the cheesecake. So it's going to get like mysteriously cut off by the edge of the bottle. And that's a rendering error you may have seen in games sometimes, right? It just goes behind this translucent thing and kind of disappears. Okay? So why not just turn off Z buffering so you don't have this problem? Well, if you turn off Z buffering and you render the bottle first, then you're just going to draw the cheesecake in front of the bottle because like you have no record of where that bottle is in space. So then you get the opposite problem, right? So with translucent objects drawn in this way, you either get the cheesecake completely cut off behind it or completely stomping the translucent object. Well, we have to solve this somehow. So what do we do? And actually, does that make sense? So let me know. I'm gonna re-up my drink. On topic, serious questions only. I feel like there's something better that I could explain about this. I'm about to say what the solution is, sort of solution. But if there are serious questions, let me know. Back to a caffeinated beverage now. Is this ignoring refraction? Yeah, I mean, if you were going to do refraction and all this stuff in back projected rendering, It's usually faked in some very sophisticated way, and we could go into that some other time. It's a whole other complicated topic, but basically, refraction is done as a per pixel operation, sort of the same way as texture mapping, the same way that you layer a bitmap onto your object. It's just you put a lot of pre-computation into what that bitmap is, sort of, I would say. And I just spilled tea on myself, so that's good. We're on a nice high-res camera now, so we can't get away with spilling tea on ourselves. So let me change out of this. See, the advantage of working from home is you can spill tea on yourself and then change into an identical shirt, and nobody will ever know that you did that. Okay. Which alpha do we use in alpha blending for interpolation? Is it a combination of the alphas of overlapping objects? Well, if an object is completely opaque, you could think of that as having an alpha of 1. And so it would completely fill a pixel. If you're rendering multiple translucent objects, you have the same problem as we're already talking about with one opaque and one translucent object. Someone says, if you represented your 3D models as voxels, could you do a better depth sort? Not really. Because the problem is, if the voxels can rotate relative to each other, there's not really a well-defined... I mean, you would have to sort on a voxel by voxel basis, which is just as slow and has all the problems as sorting on a triangle by triangle basis. If they're in the same space, if you're just saying the entire world is axis-aligned voxels like Minecraft or something, then the problem becomes different. But then there's a lot of things you can't do that we take for granted in games. Okay. So, how do we solve this? The answer is, I mean, there's lots of very complicated schemes that try to provide varying levels of functionality, but oh, and of course, let's make clear that the situation could be very complicated. Like, here's the cheesecake that we want in behind this bottle. You know, maybe there's another cheesecake in front of the bottle, right? Maybe you have a 3 beer bottle situation in between, like we just drew on the other page. Like, it could get arbitrarily crazy, right? And so what do we do? Well, step 1, draw all opaque objects. Ignoring translucent objects. Right? So drawing a scene full of opaque objects is easy. We already said how to do that. You z-buffer the whole scene. You get pixel by pixel correct sorting on surfaces. It looks great. You're done. If you had no translucent objects, you would do step 1 and you're done. Okay, so step 2, sort translucent objects back to front. Step 3, render translucent objects in this order, in this sorted order. All right? So what does that do for you? Well, so like we said, any scene with just opaque objects is relatively easy, okay? Why do we sort the translucent objects back to front? Because you want to draw the things that are furthest away first. Well, let me put it this way. Let's go back in time to before we were doing translucent objects and we were just doing opaque objects, right? Let's say we didn't have this z-buffering. Somebody said, well, doesn't it take a lot of memory to store the z-coordinates? And it does. What if you didn't want to spend that memory? What if you said, we're going to save memory and require people to tell us to render objects in the right order. Then you could still render things mostly in the right sorted order if you just have the CPU render the thing furthest from the camera, and then the next thing, and then the next thing, right? Because as long as everything that you render to a particular pixel is increasingly close to the camera, then the last value that you rendered is like the right one to go there on the screen, okay? Now you would still have this problem, this where we have the 3 overlapping objects, but you would just say, well, that's the trade-off. Like, okay, we don't want people to have to sort and clip and whatever triangles. So the CPU is just going to render object by object. The GPU is not going to Z-buffer. Just sort the objects and things will mostly be right. And once in a while, if you ever make this happen, it'll look wrong, but just don't really make that happen, right? And there were a number of games in the 90s and early 2000s that rendered that way and had corresponding rendering artifacts. But then the art of making a game like that is to avoid the rendering artifacts. So again, this is with opaque things. Now, Z-buffering solves that for opaque things. But then what we're saying is we're going to do that algorithm for transparent things and just hope there aren't that many transparent things, or hope that we're not going to get transparent things in this interlocking triple kind of situation, right? Or possibly even, I've done this before a little bit, like maybe we even just sort all the transparent things by every triangle and just say, if you're making a transparent object, don't have big triangles, which is increasingly practical now that our triangle counts are very high, right? So, first, you use the Z-buffer to get a perfect image for your opaque things. And then you render translucent things as if there was no Z-buffer. All right, does that make sense to people? Are translucent objects usually kept in a separate data structure of non-translucent ones so they can be sorted independently? Yeah. Like usually you would like have an array of things that need translucent rendering. Or, I mean, maybe if you iterate over every entity that you draw to like do some setup, maybe you just realize every frame this thing is translucent and we need to put it to the side and render it later. Isn't the three triangle issue only a problem for non-manifold geometry? No. No. You can do it very easily with physical objects in your house. How is it possible that you, don't ask. On topic questions, please. We're staying on topic. We're getting toward the end. It's been a long explanation. We're bringing it home, right? You follow, but this means that translucent stuff can't clip. So how do you do windows? What do you mean by can't clip? Can't clip to what? If you mean can't clip to the view frustum, yeah, they can. That's just like anything. What about complex objects where part of it is behind another object, but some other objects are in front? Like the 3-bottle situation, like we were saying. Well, you sort of just take the L a lot of the time, but you say, well, there's not going to be that many transparent objects in this game or whatever, right? Like there are things you can do to handle that. So what I'm talking about so far is sort of the bare minimum method of doing this that gives you reasonable results. It does not work for everything. And in fact, it does not work for everything in this game that we showed, because at the beginning, when we showed the objects that were underwater mostly, but that looked a little bit like they're above water, that's exactly this kind of case where there's actually no way to sort it, because you have a translucent thing, the surface of the water, and then you have this object that's halfway in and halfway out. And there's no order to draw those things in that's correct. You're either going to draw the thing completely out or completely in if you treat them as individual objects, right? Hopefully that makes sense. What point on the object should be used as the object's depth for sorting? You know, the answer is sort of do your best. You know, maybe you just use the origin of the object. Maybe you use the center of its bounding box or bounding sphere. If you need to worry too much about it, you maybe should do something more sophisticated, right? If you think it's really going to be a problem. But bottles itself has two sides and the edges of the bottle would be darker. I mean, that's all handled by, I think if you mean that edges of a bottle are darker in real life because of the way light acts, that's all true. And all that stuff is just stuff that you would do during rendering each pixel, just like you do for opaque objects, right? Like this whole thing that we said about, remember back here when I was saying use alpha to turn it brown? Well, you don't just give a color brown. This color is actually computed with a lot of math, just like an opaque object is, right? So you don't just like interpolate toward a constant brown. You interpolate toward the result of, you know, applying some fake refraction and light transmission through surfaces and albedo and all these things put together, right? This was a simplification just for the purposes of explaining the basic mechanism. All right. So what we've been doing in this game so far is this, and this is a pain in the butt, but we also, you know, the thing is this mostly works. It's just that we have a couple of pathological cases like these large, like if we go back to the game, let me start the game again. Most of our objects are compact. Like the character here is compact. These blocks that he pushes around are compact, like they're, you know, let me move the thing a little bit. See, like there's this transparent object in front of an opaque object, and that's fine. Actually, if I put, let me edit the level for a second. To like, I'm going to put some ground here and I'm going to move this thing behind. You can see even here in the editor, this is rendering fine. Like there's translucent thing, opaque thing, translucent thing. That works, right? One of them is in front of the opaque object. The other one's in behind the opaque object. They're both behind this thing. And in fact, or they're both behind the gray floor. And if I start adding triangles on the gray floor, those go in front correctly, right? Why? How does that work? Oh, whoops! I got a little overzealous there. Let's actually make this a different color too, because purple. Let's make it purple. Just so it's clear what we're talking about. So like, actually, okay, in making it purple, I made it a separate object, but pretend that the purple and the gray floor are actually the same object and we're rendering them at the same time, because they were until I split it to change the color. How does all that work? Well, all the purple and gray and the character and all that is rendered as opaque objects with Z buffering, right? And then when we render the transparent objects later, we render them sorted relative to each other, right? So that the further one goes first and the closer one goes second. And they're compared against the Z buffer, which is why the one in back is in front of some of the floor, but behind the purple parts that stick up. So all of this works great most of the time. The only time it's not working is when things stick through the water, like in those guys on the right in the background, except you can't see those. The time it doesn't work is these guys over here, where it just looks like they're hanging out in front of the water, when in fact, oh, actually they are right now. Hold on. Because okay, let's drop them in. There we go. So you see the opaque blocks are clearly sticking through the water, but the transparent blocks just look like they're in front of the water. And again, this would be more pronounced if the water were more opaque, but there you go. So, but this whole situation, this thing that we're talking about handled it great. And in fact, we can make this even a little bit more high pressure. Like let's just, so this is an example of like translucent, opaque, translucent, and then let's just put another one there. And oops, no, not that. We're just going to put another one of these in front, right? And it's a little bit, let's pick a different translucent object. Let's pick one of these so that it's easy to tell which is which. So you'll notice those are all rendering in the right order also. And all these particles that are inside the little energy cube. Let me drag that in. So see that? All of that is working fine because this sorting thing that I talked about handles all these things just fine. It just doesn't handle this, where you have a translucent thing, a giant translucent water plane, and they're intersecting each other. So there's actually no valid way to render it. So what I was going to do today, this was going to be a very short, in my initial idea this morning, it was going to be a very short explanation that I was going to program. In reality, this has been a huge discussion. We're going to finish the discussion, do some Q&A, then I'm going to go on a lunch break, and then I'll come back later and start programming this, okay? But to finish the discussion, if I have this case that is not working, like I have a translucent rock, like a gemstone or something, and then I have water, right? And I'm up here looking down at this with my baseball cap on my eye. There is no sorting order to draw these things, so you have to split them somehow, all right? Now you could say, well, you know, like we said, we want the game to just be able to throw objects at the GPU really fast, but in very special cases, maybe we could detect somehow that these intersect, or we can't prove that they don't intersect, and then we would sort them by triangle and send those triangles to the GPU. But in this case, that wouldn't even work. It would still look ugly because remember, like maybe imagine this is even floating up and down, like it's bobbing up and down. This thing is made out of triangles, and individual triangles are going to penetrate above and below the surface of the water, okay? So you would be by adding this expensive sorting on the CPU, you would be reducing the scale of the problem, but you would still see it. And in fact, it would look super bad because, like, for example, if you rendered this perfectly, then just below the surface of the water, you're like a little bit colored by the water, and you get more and more colored until you go down and all you see is water, right? If you render, let's say we have this triangle pointing up here, and then we have one below it pointing down. This one below it should clearly be below the surface of the water. So if we do sorting, we definitely draw that below water, but it's like kind of murky down there where this triangle starts. And this one, if it being above means that we sort it above, then we would draw this one without any water at all. So you would get a huge, this is supposed to be an arrow, not a triangle. You would get a huge discontinuity where the bottom of one triangle has no water and then the top of the neighboring triangle has lots of water on top of it. That looks terrible. So sorting by triangle isn't going to help you solve this problem. If the water level is not changing, can't you brute force a perfect triangle disposition for the splitting? Yes, but then you're dynamically generating geometry, which you might not want to do. What if the thing falls into the water? Don't you want it to look correct while it's falling into the water? Would the initial three-step approach work if you split the ocean in individual rows, one object per row? No, because okay, if we look at the top view here of the ocean, let's say the ocean is divided into squares, and each square is two triangles. This is pretty common. There's different ways of choosing this triangulation, okay? But whatever, so it's triangles like this, and then we have our object sticking through the ocean. And remember, so this part is above the squares. I started getting sloppy. So part of it's above the squares. I guess we would have triangulated this way, but whatever. And part of it's below. So it doesn't matter you know, if you render one strip of the ocean at a time, you have to deal with this individual intersection problem at a small scale, no matter what. So I think what we're going to do in this game is the following. We're going to split the object, right here. And then you can render it sorted, right? So you can render the bottom part, and then you render the ocean plane, and then you render the top part, right? So the bottom part goes in first, and then because the bottom part is there, we know how much ocean is there, so we can do the alpha blending with appropriate. This is something we didn't talk about, but there's a shader trick. Let me draw this without this scribble on it, right? So there's a shader trick where, let's say we have our object, it's in the water, we have our water level, and then we have our eye up here. Now I said before, draw transparent stuff and don't use the Z buffer, but what if you do use the Z buffer? Because like I said, now it has meaning again. If you know you're drawing from furthest away to closest up, now that Z value has meaning and you can use it. So if I'm looking down into the water, and so first I draw this, and I don't know, here's the ocean floor down here. So the first thing we draw is the ocean floor, and that's opaque, right? And then we draw this translucent thing, and that's going to alpha blend with this to give us some color somewhere in between, right? And then I draw this ocean, and this ocean has a special shader that says, look at this distance, which we're going to call, I don't know, K, because we already used D before, and pick an alpha value based on K. So if this distance is very far, it's a lot more murky. And if this distance is small, like if we're looking here, right, then it's very much less murky, right? And so that's a shader trick, is you look at the Z buffer value of the thing that's already there, you look at the value of what you want to draw, the surface of the water, you subtract them, and you say that tells you the distance, and you use that to control the murkiness. Refraction, though, yeah, that's a separate, like, we've got to simplify at some point or we will never finish the discussion. Okay. So the question is, how do you split this? Because like we said, this is a bunch of triangles, and you don't want to dynamically split the geometry every frame if it's moving. And remember, the whole point was our game engine stores these as these compact arrays. This is really messy to keep flipping back to, but our game engine stores these as very compact arrays, and that's how we want to deal with things, right? And so well, the answer is we have some advanced shader features that we could use these days. And one of the things we can do is tell the GPU, psych, I actually didn't want to render this pixel. Anytime within the shader. It's called like pixel kill, or it probably has different names in different APIs, right? And so that's what already happens in Z-buffered rendering, right? Is if you check your Z value and it's behind the value in the Z buffer, you kill the pixel. You don't draw it. Discard, yeah, it's called discard a lot. So, so what we can do is discard not based on Z, but just based on world space, right? So let's say I sort my objects. We don't have very many ocean planes in this game. This is part of what makes this practical. If we had like 7,000 different translucent planes, this would not be a good idea. But we've got like, let's say 5 in a level at most. And so if we ever detect that one of these objects crosses one of these planes, which is very fast to do on the CPU, then what we'll do is we'll render it twice. The first time we render it, we say, hey, shader, I want you to do a special pixel kill or pixel discard if the world space Z coordinate of anything in this object goes above this plane, right? And so we'll end up sort of rasterizing this whole thing, but all this stuff up here will get killed, right? And we'll just draw this, okay? That part. And then we draw the surface of the ocean and we get all this. And then after we've drawn all the oceans maybe, or actually if there's another one like up here that you could see through under some circumstance, actually you want to draw this before you draw that one. So it's still sorted. So we draw this, And then we draw this one and we put the inverse kill. We say, draw this whole object, because remember, we're talking to the GPU in terms of whole objects. Draw the whole object, but now with a shader that keeps everything above this plane, but discards everything below, right? Kills all that. Now, that's not that efficient because you had to render the object 2 times. But it works, and you only have to do it with things that are crossing water planes and are translucent. Remember, if we have an opaque thing in the water, we don't have to do any of this because an opaque thing just writes to the Z buffer, and then when we go to write the water plane later, we're just like, oh, yeah, we don't color those pixels because they're filled. It's only for translucent things that interpenetrate with other translucent things that we have to do this, and water planes are very easy because they're a plane. So it's very easy to do that math of asking whether we should do a discard, right? If you wanted to do like some gnarly rock and it intersects with some other gnarly rock, and you want to do that on the GPU with perfect intersection, it's not very easy to figure out per pixel which of those should discard. I think in that case, you would just end up pretending that one of them is opaque and rendering to an off-screen surface and doing a Z-buffer compare there and using that to do intersection of the 2 things and then render that back to the main scene after that's done. But anyway, that's what I was going to program today, and now we probably won't even finish it because we spent 3 hours explaining, but it's been fun. I've enjoyed explaining. So let's go to Q&A and comments and from the peanut gallery. Let me know what's the best cheesecake you looted last night. We handled a similar problem by rendering the whole scene without water on a texture, then render the water plane and projecting that texture over the surface with blending. It's not expensive, just an extra texture lookup in the water shader. With this technique, we also, yeah, that is a thing that people often do. So somebody said, what about refraction? And when you do refraction in this kind of back projected rendering paradigm, it often is done that way, where you render to an off-screen surface somehow that the user never sees. And then when you render to the real surface, you perturb in some way the place that you're sampling from that off-screen surface. That's like how water distortion effects tend to happen. Have I heard about weighted, blended, order independent transparency? Yeah, I mean, I've seen several. I guess the most recent proposal I saw for something like that was like a few years ago, 5 years ago maybe. And none of them ever excited me to the point where I wanted to jump up and do them. Maybe this one would, I don't know. But for this particular game, this thing that I just explained will actually solve the actual problem that we have. And so I'm psyched to do it. And we don't need to do anything more complicated. Most of these very complicated transparency rendering schemes have, they have things that they don't do correctly, which is fine if you can avoid those situations. But sometimes you don't know in advance whether they're going to be a problem for you until you try it, and then trying it is a large amount of engineering effort, and then you're sad if it doesn't work. We're staying on topic, so no design questions, no game design questions, just technical about rendering, about the things that we have covered today. Will this solution increase the minimum spec for the game? No. This is relatively cheap. Again, for that scene that we showed with 2 translucent crystals in the water and like 1 orange energy field, literally all this is drawing those 3 things twice, and that's not that much compared to all the other rendering that happens. Now, well, it's a little bit worse than that because it's drawing them twice, and when you draw them, there have to be this if statement in the shader that does a little bit of calculation and does a potential discard, and discards are not necessarily that cheap. Because GPUs are heavily pipelined, and you might just be wasting potential GPU power that you could be using on a pixel you didn't discard. Or what that gets complicated too. And again, I'm not a GPU engineer, but generally speaking, Generally speaking, for this game, this kind of solution is probably fine. This blending based on distance to surface won't work if object in the water is translucent as well. Yes, it will. Yes, it will. As long as you recorded its position in the Z buffer, which you can do, like I said, if you render back to front. And all your opaque things are already drawn. Does this also work when the transparent object is intersecting in the water? That's the entire point of what I was saying of the pixel discard. How would you do this if you didn't have discard? The way I would have done it in the old days is just clip the geometry. Like, if the solution to this problem is to cut the transparent object, you don't have to do it per pixel. That's just kind of the best way to do it. You could do this on the CPU by clipping every triangle against this plane to get mesh A and then mesh B and render those meshes separately. The problem is, it's very easy to get hairline cracks between the clip that you made. We didn't really go into clipping very much today. Again, we're at the end, so I don't want to go into it. But even if you were very careful in clipping and you made sure that the vertices on each side of the clip had the same coordinates, you have to make sure the floating point numbers are identical everywhere in the pipeline. You have to render it with the same transform and all that. And then hopefully the GPU will rasterize it the same. Maybe that's not even true because there might be something about the order of indices. I don't know for sure. But I would be very paranoid of getting hairline cracks in a clipping situation like that. But you could do that. It's also slow because now again, your CPU is dealing with individual triangles, which you didn't want to do. Right? Clipping is something the GPU is really good at. You could software clip on the GPU. So if you don't have discard, but you do have geometry shader or something equivalent to that. Geometry shader is just basically you're able to modify your triangle stream. You could render the object twice and just, for all these triangles down here, you could turn them into degenerate triangles that don't render anything. The question is, what do you do with the triangles that cross? You would almost have to have every triangle in the mesh as two triangles, or you need to have one of the later, more featured pipelines that lets you create triangles. What was the difference? It was originally, what is it called? Was it geometry shader before and then it's something else now? Like tessellator unit? I don't know what they call the things. I don't like really complicated graphics pipelines, but anyway. Hull shader, yeah. I don't remember what the different things mean. And different APIs have different terms for the same thing, whatever. But the point is, if you had one of these kind of shaders that lets you turn one triangle into two triangles, then you could actually clip this. Right? So, okay, zoom in again, right? So you've got a triangle and you want to clip it to a plane per triangle and not per pixel, right? Because we just said we don't have discard. So you would have to, do this where you turn this here and you get rid of this. And then this isn't a triangle anymore. So you output something like this. So you need to turn your one triangle into two triangles. There used to be all kinds of hacks before you could do that, where people would build meshes where every triangle was actually a quad with an extra degenerate vertex or something. And that was bananas. I don't recommend that. So you would output something like this. But again, you have the hairline crack problem. And especially if you're doing this on the GPU in like some weird stage. See, the problem is You do this one way, and then you come along later and you draw the same. This is the same triangle as that one. It's just in a second pass. And you need to do the opposite clip exactly the same. You need to throw away this part and render this little Dorito chip down here. And this needs to match this exactly such that rasterization will be the same. And to what degree you can actually do that for sure, I'm not sure. You wouldn't need to clip in such a painful way. There's fixed stencil functionality that can discard based on depth. Stop missing that message. Dude, a stencil is just a Z buffer, but not as hard-coded. That's all it is. A stencil buffer is just a number per pixel that you use to decide what to do, just like the Z buffer, right? So yes, it doesn't have to be based exactly on Z, but algorithmically speaking, it's mostly the same. Like, you don't have, I mean, unless you're going to start letting yourself have 17 stencil buffers and dynamically allocate them based on how many things you need to resolve, I don't think that that helps. Are there any first-class features you would like from shaders to make this process easier? No, I just want shaders to get simpler, and I want graphics APIs to get less stupid, and I want to be able to program in one programming language when I write shaders instead of 17 programming languages. This situation should work as long as the water is a simple shape for which you can test insideness in the pixel shader. Yes. So it could be, if you wanted to evaluate sine waves or something in the pixel shader, which is not as crazy as it sounds, due to fast approximations and stuff, you could actually have that water surface be an undulating sine wave or something and clip it. You could have it be something with an animated movie of like a texture displacement map on it that you're using to fake. That's often a thing that you do is, you know, if you're drawing water, let's do a 2D side view. Actually, this is, if you're drawing water and this is our side view like this, you're drawing a bunch of triangles that we're seeing edge on. You often fake 3D-ness to this simpler surface by, you know, like by cheating the surface normals. We didn't talk about surface normals at all, but these control the way that the sunlight reacts and bounces off the surface. So by pretending like those are not flat, you can give the appearance that this thing is not flat, especially from far away. Or you might go a little further and have displacement maps which actually modify the value that you put into the Z buffer, right? So that it's as if these things were at different heights. And then if you had like a little seagull flying really low on the water, flying this way, with his cargo of cheesecake that he stole from the Cheesecake Factory, sort of flapping behind. He's a very strong seagull. He's trying to bring this back to the seagull layer. Then, if one of these waves splashed up, it would actually occlude the seagull because it's riding into the Z buffer, right? So those are all techniques that you make to make the water look flat or less flat, but you could actually, in the case of clipping this object, if it was anything regular that you could easily compute, then yes, you could dynamically do the per pixel discard of this, assuming this is a sine wave or something. It's actually not that bad of a sine wave. The problem is actually, I mean, I guess you could displacement map this, and so you would get a consistent Z buffer. It's just, you get weird stuff like, what if I'm looking at this from way over here and, you know, and then this pixel renders later? Like, pretending that things aren't flat when they are causes a little bit of weirdness sometimes. Is this gonna just work with the particles inside the translucent yellowish block as well? Hopefully, we'll see. You can always sort particles per particle if you really have to. What was wrong with the degenerate triangle solution? It's really messy. It's really inefficient. It causes you to spend a lot more memory on your mesh, and it's not cheap to do anyway. All right, any more serious on-topic questions? Because otherwise, it's lunchtime for me. Thanks for hanging out for this whole discussion. We've had about 1,000 viewers, if Twitch is not lying to me the whole time, which is great. I hope that we've been managing to communicate some actual usual information. I don't know why I decided to do this, but I was like, you know, yeah, I'm going to explain the thing I'm going to do today. Like, it always starts with, oh, this is a programming task that is kind of self-contained, and I can do a little YouTube series on it. And then it's like, well, if I'm going to do that, I should intro it. And then for some reason, I just felt like blowing this out into a whole explanation of what happens with rendering. How does it work that you could see your character even behind objects as a shadow or something? Yeah, shadows are a totally different topic. It's actually, you could probably figure out shadows given these things that we talked about here. You could probably figure out how to do shadows. But it is sort of a different topic that has its own nuances. So that's a different time. All right. I think that's it for all the serious questions. Wait, can you instead cut out a chunk of water plane and overlay it on top of the object and render last with transparency? I mean, how do you know what to cut out? That's a very expensive triangle operation between the individual triangles of each mesh. Could you do that and would it be correct? Yes, if you figured out the hairline crack stuff that I was mentioning before. Do you want to do that? Probably not. It's probably really gross. What about aliasing with discard? That's a good question. I guess we just have to see how bad that is. You can always interpolate the discard or something. I don't know. I can imagine that there are hacks that you could do to get over that. Like you could interpolate the discard because you know you're drawing something translucent anyway. If you're mostly going to discard something, you could like just tweak the alpha, you know? It is going to be pretty bad lerp alpha instead. Yeah, but that's what I mean. Like, that's what you would do to, but then once your alpha is 0, you might as well discard because, etc. All right. Thank you, everybody, for coming by. We're going to program some of this later. I think my first step is just going to be to program the discard, or the suggestion just came through to not discard at all and just tweak alpha down to 0. You know, those both involve doing the same test on the GPU of plane versus object. And that requires the CPU to notice that those things potentially intersect and so forth. And so we're going to try to do a lot of that today. And we're going to see how far we get, etc. So thank you for coming by. And did I finish the cheesecake? No, but I'm going to enjoy the remainder of the cheesecake as my reward for doing this explanation. And see you all later.